live, so hello to everyone that is joining us live or watching the recording. We're going to be getting started now, so I'll unfreeze the screen for those of you that are here in person. Again, if you want to scan the QR code, please do so. The font is working now, thank you. And apologies for the wait, we just had some technical difficulties today. Let's see if I can really get going. So sorry for the wait, we had some difficulties with our calendar and our organization, but we have sufficient amount of time today to go through everything that we need to go through, want to go through. So what is going to happen today and what's not going to happen today? That's the first thing I'll try to explain. MATHSoc and recently CPMSoc have been doing these types of revision seminars in the past. The way that they kind of work is we'll go through a lot of different pieces of content and questions. So we have examples of these questions and content that we'll go through in just a second. What we will be doing is going through those basically throughout the whole course. If you have any questions, please ask them. But I do want to emphasize that for the context of, I guess, this course in particular, as you're aware, the way that the exam will be working is all the questions will be from either definitions that Dennis will ask or questions that will be from the shortlist that he's posted. We haven't put too many shortlist questions in our slides today because we think that demonstrating how to do those is probably not the best way for you to learn and to do better in the exam, because you can certainly practice those questions yourself. What we're going to be trying to aim towards today is give you the chance to recap the intuition and the broader scope of what we learned in this course and how we can use that to help us when we're approaching the specific questions that Dennis is asking for us to remember for the exam, along with helping you try to remember what definitions are important, how do we approach these definitions, how can we remember these definitions, and for me, the best way to remember that is to have this strengthened intuition behind what these definitions mean in the scope of the course. So this is more or less trying to tell the story of the whole course. We have a few examples, we have a few questions. Apologies, some of these questions are a bit outdated. We have sourced them from previous exam papers. I find some of those questions are interesting, and if you want to, I do encourage you to have a go at some of the past exams that Dennis has posted online, even though a lot of those questions are not in the current syllabus of the course, but again, they do kind of fit into the overall scope of what we are learning with this course, which is analysis. Can I check the stream is okay? It's not done? It's on the other end.
What?
The CPM.
Oh, you're doing the CPM. Oh.
We'll check the stream, but hopefully it's all fine. But otherwise, any other questions before we get going? Okay, cool. We'll get started then. I guess I'll introduce myself first. So I'm going to be presenting the first two chapters. We kind of split it up in, I guess we don't have a table of contents, but the way we split it up is we're looking at sets and cardinality, then metric spaces. I'll be covering those, which encompass, I believe, the first 4 or 5 weeks of the course. Jeff will then take over for the topic that focuses on series of functions and the introduction to topology, and then Daniel will finish us off with compactness in the last session. We'll have a big break in between, so roughly 3 o'clock, and we'll try to have pizza near then. And we'll split that up when we get up to that point. But we won't try to overwhelm you too much. We'll try to go at a smooth enough pace. If you have any questions, again, please do ask. Again, the QR code is there. You haven't scanned, but I think you all have, by the looks of you. Let's get started on the content then. So we'll try to start by looking at this first. What was the first week of the course, where we focused on a few ideas involving sets. I mean, looked at particular ideas revolving around cardinality of sets and what we can do to say how we can compare the size of sets. So the important notions to us, I guess we could start off with. We're going to start off with a few definitions and I guess the most important theorem for this part of the course, which was the way that we can talk about how big sets are in comparison to other sets in terms of particular types of maps. So when we're looking at two sets, the interesting question we can ask is, in a sort of intuitive sense, is set B larger than set A or vice versa? So the way that we defined it in the start of the course is we looked at injective maps. So we said that if there's an injective map from A to B, kind of intuitively that's saying we can fit A inside B. So sorry for the drawings in the first half. I'm not too used to the stylus. So we can map A into B injectively. Remember, injectively means that no different elements map to the same element. And we learned as well that assuming axiom of choice, that this is equivalent to saying that there's a surjective map from, I guess, B to A. It's kind of weird the way I've written it, apologies. But we would say this is equivalent. I'm just going to write it here. This is the same. This also means, actually, I'll probably apply the double arrows, implies there exists a map G from B to A such that that is surjective. And again, this is assuming axiom of choice. And that's one of the questions in your first board tutorial chief. So that's one that I would recommend you would revise. So one other thing I'll try to do, at least in my section, is to recommend the particular types of questions that you should revise and have a look at when you're approaching the different parts of the course. So just want to mention choice. Okay, and then we defined what does it mean to have sets of the same cardinality. That would mean there's a one-to-one correspondence between them. In other words, we have a bijection, so a map that is surjective and injective, objective map. Between the two sets, we said that they have the same cardinality. Remember, when we're dealing with all this, we are dealing with sets that are not necessarily finite, for at least when they are finite. Hopefully, have your intuition work when they're finite, in which case this makes a bit more sense. And when we're dealing with infinite size sets, when this is more of a formal expression, so A is not necessarily a number, but it's more of a formal expression. It may not be finite. Be a number. It may be a formal expression. You can't get what I mean by that. And in that way, what we care about is we're abstracting this idea to compare the sizes of sets to functions. Okay, so similar to what we do with a lot of things in this course when we abstract the idea of open sets and topology, it's similar here. And then we have this notation, we don't use it much, but when we have the size of A is less than equal to the size of B and they're not equal, then we have this strict notation. Okay, so moving on to the, I said before, it's one of the important theorems, but I'd say it's more of the, it is of course on your problem shortlist for week 1, and it's probably the most difficult proof in the course that is by Dennis going to be possibly assessed in the final exam. So please do try to know the proof of this theorem. But what it basically says is that this relation of when we're comparing the size of sets is a, I guess you could say an equivalence relation when we're dealing with the, well, it's well defined in the sense that one thing you can also prove is that if you have sets A, B, C, what I mean to say is that if the size of A is less than or equal to size of B, and size of B is less than or equal to size of C, you see what I'm getting at soon, then the size of A is also less than or equal to size of C. And what this is saying is it gives you this sort of, it does give you this anti-symmetric property if you think of this less than or equal to as a relation. So what this says is that you're dealing with a the sets and the relation of the cardinalities comparing each other would form a partial order. The other thing you'd have to verify is the reflexivity, which follows because you can use the identity map as your bijection. So that gives us this nice way to think about this comparison between the size of sets, forms a partial order. Looks from here. So this gives you anti-symmetry. Another thing that we want to know is the axiom of choice. This itself is, I guess, not too difficult to use, but I guess when I was first learning it, especially a couple of years ago, to get a grasp of what it really says is a bit difficult. But in the language of this formal mathematics where we deal with Cartesian products and thinking of Cartesian products as functions, then it's not too difficult to reason with. What it says as a reminder is if you have a collection where, again, similar to, say, topology, this index set I may not be finite, it may be countable, may be uncountable. If you have this collection, though, indexed by this index set I of non-empty sets, then the Cartesian product is non-empty. So what does that mean? It means there is an element, and I'll call this, you can think of this as a function, f in I, index set Si, and the particular use we use for this, well, as I said before, it's useful when showing this property, assuming axiom of choice, that if there is an injection from A to B, there's a surjection from B to A. We can think of this f as a function. F goes from this index set to, I guess you could say it's the kind of union of the Si, but in particular it says that f of I maps to f of I is within Si. So maps one of the indices to an element inside of the corresponding set for that index. Okay. And so another important concept when we're dealing with sets is talking about if they're countable or uncountable. So what we kind of do is we take the natural numbers, which are very important to us, very foundational, and we say, we kind of draw a line in the sand there. So we take the natural numbers here. We say that everything to the left of the natural numbers is countable. And we say everything to the right is uncountable. In particular, if we have an infinite set that is countable, we say it's countably infinite, and otherwise we say it's finite. So finite is, in the way that we understand finite would be, finite is the size of S is the same as the size of some sort of index set, 1, 2. You can think of finite sets in this way. To n for some n. And just a reminder, in the beginning of the course, not that it's too important, we did talk about this concept of Dedekind finiteness. That turned out to just anyway be equivalent to the finiteness that we intuitively understand, but a useful result from that was that you could characterize an infinite set as a set that has a bijection between itself and a proper subset of itself. Okay, so that's another exercise I recommend that you remember how to learn. So Dedekind infinite was bijection between S to a proper subset of itself. Try to prove that that's equivalent to our usual definition of infinite, or usual understanding of infinite, and how that corresponds to the opposite saying Dedekind finite is otherwise, how that's consistent with what we understand, I think to say. Okay, let's take an example now. Dealing with countability, let's take the set of increasing sequence of natural numbers. So for example, we could have a sequence that is, say, 1, 3, 6, 7, 12, ... We want to decide whether it's countable or uncountable. So we'll try to look through that, and we'll try to look through how we prove something like this result. So hopefully you have this type of intuition by now in the stage of the course. Hands up if we think countable. Hands up if we think uncountable. Okay. Wonderful. Yeah, so we can think of this in a few different ways. You can kind of think in a certain way, since we're dealing with strictly increasing subsequence, you can think of it as, say, the subsequence that is the kind of identity in a certain way, 1, 2, 3, 4, ... plus some A, B, is how when I was trying to approach it intuitively, this is how I thought of it, where you're saying A, B, C are in natural numbers. So in that way, you can kind of, if you just restrict at least A, B, C to be 0, 1, then you have this bijection at least to not a bijection, but a surjection to the set of bit strings is one way you can think about it. We've written out the another way you can think about the proof is one important way that we looked at the start of the course in proving that a set is uncountable, which was the Cantor diagonalization argument. So if we do the same, if we try to play the same game here where we write out a series of strictly increasing subsequences, I keep saying subsequence, too stuck in computer science. And what we can do is the same trick where we look across the diagonal, we use the diagonal to try and construct a new increasing sequence that's not represented in this this grid. This is 0, 1, 2, 3, dot, 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 2, dot, dot, dot. And this is the position, so index 0, index 1, dot, dot, dot. We want to build a new sequence that contradicts the way that this supposed function that is attempting to enumerate this set of strictly increasing sequences by having the specific way we do it is we kind of bump up every element. So we take the first element of our sequence to be one above the first index of the first labeled element, and we can continue to do that to make sure, first of all, we make sure that it's increasing, and then we add an additional, these two components, one make sure it's increasing, the other make sure that it's not the same as the diagonal element. So this to ensure any questions so far? Any issues, concerns? Okay, nice. And yeah, we have this small little question here, which is kind of asking for us to look at playing the same game as what happens when we, an exercise again is looking at what happens when you take some sort of product or some sort of union of countable sets. In particular here, we have this Cartesian product of countable sets. So a finite Cartesian product of countable sets. This is countable because what we can try to do is to use induction, perhaps because we are dealing with finite fixed n, we can use induction. Basically what we're arguing is if A be countable, then A times B countable. So this is a classic type of argument that we've done earlier stages of the course, where we list out A and B on two sides of the grid, and I guess one visual way to refer to what we're doing is either going along the diagonal or what you may call dovetailing. There are other different ways to approach it, perhaps depending on the structure of A and B, but this is the general way to do it. You can go along the diagonal, you can dovetail. Specifically, the way you have to formally write this one out, I won't spend too much time on it, but you say that since each of these sets are countable, you know in particular there is a map corresponding to them that is like the counting function that has this correspondence between the natural numbers. So what you're showing is, you can show, what we kind of start off with showing is that the size of this Cartesian product, Si, is less than or equal to the size of the 1 to n, the natural numbers, and then you can show that's the same, so the same as the natural numbers. So in particular, you get by this transitivity that we work with when we're comparing the size of sets, that then you can say that this set we're looking at, which is S cardinality less than or equal to the natural numbers, so it's cap. And so specifically, we have this set of functions that gives us correspondence. This injection is the way we think about it. This injection, and we can show, yeah, the Cartesian product of natural numbers is countable by induction. And we have the details written out here. You go inductively have this function and you bump that up. Let's see, how much do I want to write out? Yeah. I'll just move on from that. Any questions on that one? Yes.
So back to the previous one. Second as well.
This one, you mean?
Yes.
Yeah.
So my intuition is to think of this as a tuple of natural numbers and a sequence. So for example, we associate the number 1, and then on the other side of the tuple is a sequence of when number 1 appears. So if it appears in the second and third sequences, and that will the set of those tuples describes the set S itself. You follow so far?
So you're saying, maybe if I'm getting you correctly, if we had, actually maybe no. You're saying, are you looking at the index at which the elements appear?
So we don't need to index them within each sequence because we know the sequence is well ordered.
Yep.
But we do need to index in which sequence they appear.
Okay, sure.
So yes, I'm looking at, let's say, the number A,
Yep.
where in which of the increasing sequences A appears. So that would be a sequence. That's a tuple of the letter A, and then the sequence of where it appears.
Yep.
Both are clearly countable. So both are only made up of natural numbers. And now I have a tuple of two sets of the tuple countable set and countable set. And from our next question, now that it's not a Cartesian product per se, because our two sets are different, but it is the product of the two countable sets.
Right, I see. So you're saying you can fit this set of increasing sequences into data that gives you a way to say that it is countable. But that's assuming originally, though, that it is countable, because you're saying the idea of which sequence it belongs in.
So we know that the choice of elements is countable.
Yep.
You told me it's natural numbers, correct?
Assuming that this set of strictly increasing sequences is countable, then you could have this the set in which you're looking at, in which a particular element appears in, is countable itself, yes. But otherwise, assuming that it is countable in the first place, then you can have.
So yeah, if we have a countable number of increasing sequences, then it's countable.
Yeah.
If we have an uncountable number of increasing sequences, it's not countable.
Sure.
Okay.
And that, I do think that's an interesting thought, and it does help you understand. But in this case, if you have a countable number of increasing sequences already, then you know it's already countable.
Yeah.
Okay, good. Okay. So we'll skip this one, details on the slides if you want to look through it rigorously. We'll move on. So this is going a bit further than the previous result. Another one. The proof is a bit more, shall I say, bookkeeping than anything, but this is very similar to the previous result, very similar to this dovetail argument. That if we take the countable union of countable sets, then this itself is countable. And another important result that we looked on earlier in the course that gives an alternative way to prove that the set of set 0, 1 is countable. You can use this result. Because what we do is we represent every number within 0, 1 as a sort of bit set for natural numbers. And we use that to derive a contradiction based off this result. So moving on, this will be the last question, I believe, for this topic. So this is trying to get towards, again, this idea of how do we put our fingers on working with countable or uncountable sets, how do we say precisely say what the details are of what a countable or uncountable set looks like? For this one, I will say it is countable. I'll just go through the answer briefly. The idea is that we're given a set of solutions to equations of this form for any n and m. The idea I want to get to is that with this structure of this kind of being indexed in a certain way by these numbers, these integers m and n, the restriction that puts on your solution is that since we're dealing with a quadratic, you get at most 2 solutions for every pair of integers. And so what you're working with is that you can look at your solutions as something corresponding to the set of tuples of integers. And so specifically, you're dealing with some sort of space of solutions that is roughly equal to the size of roughly equal to z times z in a certain way. And that's countable. So let's be a bit more precise. The technical way to approach it would be to say, okay, for given m and n, we can get a solution. We can always get a solution in this form if we express it algebraically. And so we say that we get 2 solutions based off each of the values of fixed n and m by the quadratic formula. And so what we can say is we can index these solutions if we wanted to be make this quite general argument where with this plus or minus that we have up here, we could even just take that as -1 to the power of k. We're kind of working in a larger space than we really need to, but that's fine because we could still make this starting from this collection of, let's say, indices, 3 copies of z. So it's Cartesian products of 3 copies of z. What we want to try and do is make this surjection, so we can hit everything from these copies to the set of solutions. So we're trying to say that this is going to say intuitively the way we work with sets always going to be try to deal with a function that gives us a relation. In this case, we want to say that the size of S is no greater than the size of this Cartesian product. By this mapping, we go from these indices to our solution. And so what we can say from there is, as we know from the reasoning we did before, the set of integers is countable. This should be face n. The set of integers is countable. And so we can map from this Cartesian product of 3 copies of the set of integers and compare that to S. So S is less than or equal to size of n. Okay. Yeah, sure. So let's continue. So now we're looking at metric spaces. So this will be the other topic I'll be taking you through. So metric spaces are an important part of the earlier stages of this course because they give us one beginning way to look at one important topics in analysis, which are how do we generalize these notions of continuity of functions, of convergence, of limits that we learned in earlier years of, say, first year calculus, and how do we deal with those same notions? How do we deal with notions of what sets look like with respect to this particular, in this case, metrics, and how that impacts certain results we can get based off continuity. So the main one in this course that we built up to was the fixed point theorem, which then we used in the Picard-Lindoff theorem, which is one of the ones in your shortlist for the final exam, I believe in week 4. And so yeah, let's build through that. So remember, what's the definition of a metric? So this is, say, one of the simple examples that Dennis might ask for the final exam. Make sure to remember and understand why each of these are important. So remember, a metric, intuitively we say, gives a distance between 2 objects in a set. So one important thing to remember is a metric space is not necessarily a vector space. So a metric space is just a set X3 may not be a vector space. So it's only when we get to talking about inner product spaces or non-vector spaces that we actually start caring about if there is a vector space structure. So for now, though, metric spaces, we're just dealing with this distance function. And what we need is we need three properties. We need this positive definiteness, that's to say, what we know already, that dxy is greater than or equal to 0. We say that it's 0 if and only if x is equal to y. We also want to say there's no bias between going from x to y and y to x. Y. Same each way. So that's your symmetry. Triangle inequality is the last one. If you start at x and you go on a detour, then that should not be a shortcut instead of just going the straight path to y. So triangle inequalities are very, very important in analysis. So be prepared to use that in a lot of your proofs. And in total, yeah, we look at this as our metric space. So what should you have in your back pocket to work with when you want to find an example, a counterexample, or just anything that you want to do when you're dealing with metric spaces? What are the important ones we want to deal with? Well, I've tried to outline, I guess, some of the most important ones, at least to me, when we're dealing with, I guess, some basic spaces. If we're dealing on, say, Rn, then we have the P metric. So when, say, P is equal to 2, that's our normal Euclidean distance that we're all used to. But we can generalize, and hopefully by the end of this course, you are now loving these types of different P norms, that we can have a lot of different spaces. So we can not just have this in Rm, we can also have it in sequence spaces and also in spaces of functions when we're dealing with replace the sum with integration and this finite sum with an infinite sum. So just be aware that we do care about this P norm. Remember, we raise the power of P in our summation, sum n, and then normalize everything with 1 over P. We also care about the discrete metrics. So the discrete metric would be usually your pathological example. A lot of your results, your naive attempts, may fail in the discrete metric. The discrete metric is a very simple one. The discrete topology in the same way, very simple. And then finally, the infinity metric, which is basically what you get when you take the P metric and you send P to infinity. You get the infinity metric, which takes the maximum of all your components. So when you learn this the first time, it might not make too much sense as to why it has this structure, but it's a very, very important one for our uses, especially when you're dealing with functions. So some inequalities that we need. Remember, equalities, again, are the very important tools that we need for dealing with analysis. One particularly important one is called Minkowski's inequality. So this is one that, strangely, the proof seems to be examinable based off what I've seen in the shortlist, because one of the questions hints at using Holder's inequality, which is how you prove Minkowski, which was done in lectures, if you want to revise that. But what Minkowski basically says, and it generalizes to when you're dealing with function spaces and to sequence spaces, is that when you have this, well, basically says that this P metric is well defined, as in it satisfies the triangle inequality. That's what it says. It's written in this way is the result. And as I said, the proof of that involves what's called Holder's inequality, which was something that was briefly mentioned in lectures and used for this proof. For those of you that did 271, I was also mentioned there. The basic idea is that if you have these numbers, which are called Holder conjugates, P and Q, which satisfy this sort of normalization condition, then you get that this dot product, so I'm saying dot product because if we're dealing with Rn, then it's a dot product, is less than or equal to this weird product, which what this looks like is, it's basically, you can think of it in two ways. It's the distance from 0 of a vector x in the P metric, like this, times the distance from 0 of y in the P metric, Q metric. And you can also think of that in terms of norms. So in the P norm and Q norm, which we'll get to a bit later, P and Q, it becomes this product norm. So it's a very nice inequality. And as I said, convergence is one of the very important ideas when we talk about metric spaces. So metric spaces give us this first way to look at what does it mean to converge in this space. So what does convergence mean in a metric space? Intuitively, a metric is talking about the distance between objects. So this is saying, if we draw a circle around X, we're saying that the distance between X and our sequence eventually gets arbitrarily small. So say, if you look at the epsilon definition, for any size, you can eventually find a natural number such that when your sequence is past that point, it is stuck inside of this ball of that radius epsilon. It's epsilon here. Epsilon. It's stuck inside of this ball of radius epsilon and it can't get it. Okay. One other thing to note is that unlike topological spaces, metric space limits are unique. So remember the proof of this. This is one of the very fundamental proofs you should be able to work with yourself. So if we had a limit x1, a limit x2, the way that we deal with this is that, if you remember, we need to do something that works in metric spaces to do this. The way that we do that is we think about, well, there's this distance between these two limits, x1 and x2. And what we basically do is we set that as our epsilon when we apply this definition, and we derive a contradiction, I suppose, by the triangle inequality. We'll leave that as an exercise for you to write out. And then, yeah, what I mentioned otherwise is we have this definition, these definitions of we're about to get to, which is open and closed sets, which are important when we're trying to characterize, I guess, what our space looks like. And so fundamental to those is these different definitions of interior, boundary, and limit points. So remember, a ball of radius epsilon, I did mention it before, but specifically around a specific point. So what Dennis typically likes is for you to call that point x0. So when if you're fixing a point, it's good to put a little naught subscript under it, just to say it's a fixed point. Well, not a fixed point, but a point that you've chosen is not an arbitrary x, whereas here we're saying x. Otherwise, such that the distance between that and our specifically chosen x0 is less than epsilon. What it means for a point to be interior in a set Y is if there is a ball of radius epsilon that fits entirely within Y. So you can kind of expand a little bit outside of x0 and you can still remain in Y is what that says. Boundary says that every time you expand, so if we have this set, I'll try to color code this properly. Boundary, visualization, every time you expand, you get points both within and without this set Y. And then limit point says that every ball of any radius epsilon contains some point of Y, different to the point itself. Okay. So a limit point there may be points in Y that are not necessarily limit points, such as isolated points. But if you have any point that is non-isolated, any point on the boundary that's not in Y, then it is a limit point, as an example, and any point that has any point in the interior is also a limit point, is an example. And we can use this ball of radius epsilon to define boundedness. So remember, one result we saw in class was that we have 3 equivalent conditions for boundedness, nicely enough. So we can think of it, first of all, as this for any point x, there is this radius such that the entire set Y, if we draw Y here, is contained in some ball of radius Rx. Or you could say equivalently, it is such that there exists a I'll call it Y naught actually. Y naught, to be a bit more precise, there exists one fixed value Y naught in your set Y such that it's strictly contained in that ball of radius R. Or you can also say is that such that every pair of points, their distance away from each other is bounded. So this gives you a lot of different intuitive ways to think about this. So the first one saying eventually for any point you can get far enough away such that you've encapsulated Y. The other one saying that everything's contained within one specific point in a given radius. And the third one is saying that you have this bound on the distance between points. So boundedness is a very important assumption we deal with a lot of important results, particularly when working with functions. And then, yeah, we care a lot about these open and closed sets. So remember, open sets, the way that you define them, there's equivalent ways to define them. First is every point is an interior point. So every point has a radius epsilon. This, say for all x, there is this epsilon with 0 such that all this epsilon is within y. And you could also say it contains none of its boundary points. That's a good way to say it. For closed sets, particularly when you're dealing with topology, the important concept to understand is that they are the complement of open sets. That's not to say a set has to be either open or closed. A set could be both. It could be neither. Say if it contains half its boundary or none of it. We could also say one important result that we have in metric spaces that doesn't necessarily work for topological spaces unless you use nets is that a set is closed if and only if it contains all its limit points. That's another way to define it. Okay, and so for at least for now in the scope of this part of the course in metric spaces, the way that we define continuity was saying that kind of taking what we learned in first year calculus and extending that a little bit in terms of replacing the absolute values with our generalized metric. So we're saying for all points, if we get close enough to our point, then our function value isn't too far away from our evaluation of that specific point. So that's to say for all epsilon there exists delta, the classical trait that we have, and I'm sure you're very familiar with this. But what we work towards for topological spaces is that instead we can think of this as what's equivalent, and something that you can prove again yourself, is that this is the same as saying that the pre-image of an open set is open. Okay, so if you say intuitively pull back open sets, go from a U back to an open set image. Okay. And going from metric spaces, we can also define norm spaces. And then later we'll define inner product spaces. What a norm space is now we're working with a vector space. Remember before, metric spaces aren't necessarily vector spaces, but norm spaces are necessarily vector spaces. We have the same rules in a certain way. Specifically, when we have a norm space, then that gives a metric. So a norm space has an induced metric. The converse is not true, because we have sort of slightly stricter conditions on what this looks like. First of all, it has to be a vector space itself. So if you're trying to look for an example that is a metric space, but not a norm space, go to one could be, say, I was trying to think of one before, I guess, give any space that's not a vector space. For example, the set of vertices of a positive weighted graph is a metric space if you give the distance as the sum of the path, the shortest path between vertices, but that's not a vector space. And the difference, besides triangle inequality is still here, this positive definite is still here. The different result now is we have this sort of homogeneity. And the reason why I've said lambda is in R, this does work. This does work when you're dealing with the complex numbers itself, but this course is called real analysis for a reason. We do not care about complex numbers. So let's try ourselves with this question. We want to determine if it's open and closed. So let's try to visualize this. We have this union of these different balls. So we can write these. This is a union of balls that look like centered at some point x. Oh, sorry, forgive me. Centered at the point 1 over k 0. And they of radius 1 over k plus 1. So this is lying on, balls of smaller radius, smaller and smaller radius on the x-axis. So we have, say we're starting with when k equals 1, this is 1 of radius 1/2. So this goes to, say, 3 over 2. It's 1 over 2. Here, so it's the start. And then we go to 1/2. We have radius 1/3, like this. And we keep going, smaller and smaller. And what we want to look at is if this is open and closed. So one thing we can observe is this point. I guess I should have drawn this dashed since they are open balls each. Actually, no, I was correct to draw them as undashed because these are closed balls, she said, because we have this less than equal to. So we do have that. One thing we could say, first of all, we have the set y includes the furthest point to the right, which is 3 over 2. On the x-axis, the boundary point, 3 over 2, 0. So that's one thing we can observe. So that gives an argument as to why it wouldn't be open, because open sets, every point is an interior point. We have this boundary point, so that gives an argument as to why it wouldn't be open. Let's think about if it is closed or not there. So let's try to make a comparison. Well, one thing I could maybe think of is, are we ever going to, this drawing might be a bit misleading, so I'm going to ask, are we ever going to miss out on any limit points? So one possible candidate for a limit point could be the point 0, 0. So let's see. So let's look at an arbitrary 1 over k. 1 over k 0. And we have this radius k, 1 over k plus 1. And so always in each of these balls, this point 0, 0 would be close, but it would never be hit by these balls specifically, it seems a bit. And so basically the argument would be that it's neither open or closed. It's not closed because it doesn't contain the limit point 0, 0. It's not open because it does contain the boundary point 3 or 2, 0. So let's have a look. It's not open. So the answer's here. Each ball does not contain 0, 0. I should have argued a bit more as to why that is a limit point, but the intuition is here. You're getting closer and closer to it. I guess if you take the centers as they go smaller and smaller, because you'll contain at very least each of these points 1 over k0, you can build a sequence inside of this set 2, 0, 0 that converges in this usual Euclidean metric of R2. And so that would be why it is not open or closed. So it's not open, not closed. So at this point, I think, are there any questions? So most of this would be revision from previous courses as well. But any questions? Okay. Yeah, so we looked at norms, and now we can also look at inner products. Getting towards the end of the definitions for this chapter, but inner products, the next step towards next, I'll draw a picture later when there's a particular slide I want to draw a picture in. Inner products are kind of a stronger version of a norm, is the way I'll say it for now, because what they do is they induce a norm. If you think about this as the normal dot product in Rn, then this works in the same way as usual. If you take the square root of the dot product. So basically what you have is you have this cute face that goes from the Cartesian, it's a function that takes 2 inputs, and it's bilinear, gives out a real value, because again, we're not going to worry about complex numbers here, though you can generalize, we're dealing with real inner product. So we don't really care about the complex numbers in this course. So I guess thinking of it, there is a short list question that does involve. Let's say C for now. Let's say F. F is, just to be precise and not mislead you, F is either R or C. And all that changes is that there's this conjugation when you're dealing with the complex numbers. So specifically, this is mapped to the field, the vector space is in front. So, but yeah, really in this course, besides that one question I'm thinking of, the only scope we need is for the real numbers. There is this very, very small question I have in the back of my mind involving applying Cauchy-Schwarz to one of the shortlist questions for complex case where there was conjugation, but that's not very important to us. And inside of just any metric space, the reason why I have it here is because I want to talk about the definition of Hilbert and Banach spaces, because this coming to the very important concept analysis of completeness. Having completeness in your space is very, very important when we're talking about looking at convergent sequences, because we want to be able to use what's called the Cauchy test, which will have in a later slide, for looking at convergent sequences. So in particular, a sequence's Cauchy is if when you have large enough indices, you take any pair of them above a certain value, they are eventually close enough to each other. So that's to say the sequence values, K and L, are eventually close enough to each other. So completeness defined of that is to say every Cauchy sequence converges to an element in your space. So for example, R is complete. And there's two types of metric spaces, two types of important definitions of complete spaces that are metrics, that induce a metric. So this is the type of picture you can have. You can have Hilbert spaces, which are complete inner product spaces over R. And remember, Hilbert spaces, they work in inner product spaces, which then they fit inside. How do I want to draw this? So remember, they fit inside our norm spaces, the norm vector spaces. For consistency, we have to draw something like this, which is then to say our Banach spaces are complete inner, which is very hard to draw. Maybe I'll change this as here. And I'll say we have some sort of image that looks like this, where Banach spaces would be our complete norm vector spaces. So these are Banach. It's Hilbert, it is also Banach. And then these are all fitting inside of our metric spaces. And then metric spaces fit inside of our topological spaces. Metric spaces are examples. They induce your topology of open sets and closed sets. Remember, OX, set of open sets in the metric. Because when we started this course, we looked at a lot of the different properties of, say, take a arbitrary union of open sets as open. That gives you the fundamental properties of topologies. For spaces. So that's the next step up. So we spend part of this course looking downwards into inner product and Hilbert spaces and norm vector spaces. And then in the second half of the course, we look upwards into weaker notions. Okay, so getting towards some more, some results actually in completeness, some important ones to know and to understand the proofs of. Say, for example, one important one is when we deal with, say, the space C01 is complete. When we deal with the infinity norm. So that's an example. So since it's a norm space, it's a Banach space. Since it's complete. And we have other ones here. In terms of ones that are not involving functions, some important sequence spaces are the LP space, which is a Banach space because it has this norm that you define in the same way as your P norm, and now it's an infinite sum. Likewise, you can have the L infinity space, which in a similar way is what happens when you say P to infinity. This one's a bit easier to work with since you're working with the supremum, but now it's the supremum over an infinite set. So instead of for Rn before was the maximum, now it's more of the supremum. So now it is the supremum that might not necessarily be obtained, so not just the maximum. Again, it is a Banach space, so that's enough for us, which is why we care about a lot of the spaces. And this one's just to revise some of the spaces we do care about, which is C0 and C double naught, which appear, you can think of them as what they are, subspaces of the LP space. And for one of them, specifically, you run into trouble when you are dealing with the, when you deal with the space C0 with the L infinity metric, the L infinity norm, then you are okay. But when you deal with the P norm, then that norm might not necessarily exist. And so it's not really proper to say that C naught is a subset of L infinity. I think we can draw a picture, or we can say that, well, if we take any LP, L infinity, then we have inside of that we can fit in if we want to. Let's see, we have C naught and C double naught, whereas for LP, we could have, let's see, C naught would be somewhere here, and C double naught would be here. That's what we need to say. We have some results. One interesting difficult proof we looked at in class, you might want to revise again, is that when we deal with the L infinity metric, then the closure of C double naught is C naught, whereas for LP, if you take any P, the closure of it is the entire space. So that's to say, C double naught is dense in LP. That's a different result, which is quite interesting. And these are the definitions here if you need to revise. C double naught is when, and usually Dennis would give you this definition in the test because it is sometimes hard to remember. I believe he did that for class this once. But C naught is when the limit is 0 for the sequence, the limit of the values, whereas C double naught is when the sequence, I guess you could talk about the support if you're familiar with that concept. The support is finite, but that's to say the sequence is non-zero only for a finite number of values. Okay, these drawings. And Dennis's favorite Cauchy test that he loves saying in his lectures is a good way to show that a sequence is, I guess, not Cauchy if it fails its Cauchy test, which means to say, and also if you're dealing with a complete space, passing the Cauchy test does give you convergence necessarily. So what is the Cauchy test? This Cauchy test says that if the limit as you pass n and m to infinity at the same time, so that's to say you're looking at m and n above a certain k, then this expression should approach 0 for the sequence to be Cauchy, and that's really just another characterization of being Cauchy. Okay. And it's a necessary and conditioned convergence in a complete space. Okay. Yeah, so we're going to have this question here. I'll briefly look through it. It's not too appropriate for the course in its look this year, but just go through it briefly. It's basically this idea of, again, we haven't really defined orthonormal sets in this course or worked with them too much. That's a nice little question if you want to have a look in terms of Cauchiness, because this does give a nice example of what happens when, typically when you try to look at sequences in Hilbert spaces. Well, what we're doing, first of all, is we're taking this, you can think of this if you just want to, as the set of standard basis vectors. So specifically, it forms an orthonormal set. What we want to show is that first of all, the sequence defined by the kth element being this kth basis vector in our orthonormal set. We want to show that that's not Cauchy. I'm saying basis because if it's an orthonormal set, then it might not necessarily be spanning, but actually it won't necessarily be a basis, but it will be linearly independent, is what I mean to say. So it's not Cauchy. Why would that be? So if we look at Cauchy would mean that we could always bound what x, let's say x, x, I won't use n, I'll use k and l. So it's xk minus xl. We're dealing with this Hilbert space. So we have this norm. And when we're dealing with Hilbert spaces or we're dealing with any norm space, we talk about the metric induced by the norm. So what does this look like? And in an inner product space, the norm is induced by the inner product. This looks like the xk minus xl, xk, so I'm going to say k is not equal to l. We're going to use the property that this is an orthonormal basis. It's a bit more linear algebra than anything. xk, I'm going to assume this is a real, this is a Hilbert space. xk squared minus 2 xk xl. So this dot product will be 0 because we're dealing with an orthonormal basis, and then plus xl squared, so this is 0. And then we get each of these are 1 because we're dealing with orthonormal, they're normalized. It's 1 plus 1, so that's 2. And so we could say if we choose our favorite epsilon, this can't be bounded by that epsilon. So that's the basic idea here. And then in part 2 of the question, if we have a look briefly, what we want to do, so we did that. What we want to do is show we have this sort of, in this case at least, this result that resembles the Pythagorean identity in a certain way. And so what we could do is this comes out mostly algebraically. I'll just leave out the details here. So we can rearrange our definition of Zn, which is our remainder when we express y in this sort of Taylor series way, when we try to get its coordinate vector. We get this large sum. If we express it out in terms of this whole sum, if we expand everything and use the linearity of this dot product, we have exactly sum here. Basically, the result follows from using the fact that for non-equal indices, the dot product is 0, this inner product is 0, and otherwise it's 1. And so the sum that we get becomes this way. So again, that wasn't too important to us. This one's a bit more important. We've got an intuition behind what we typically do. So this is a useful space for us. Again, this is what I said before. We're dealing with the uniform metric, d infinity. So we'll call d infinity from G. This is supremum. In this case, x in 0, 1 of f of x minus g of x. We want to show that this is a complete metric space, or we want to either argue that it is or it isn't. And so what we're dealing with is a subset of C01. We know that C01 is complete. There's a nice result that I've written on the next part of this slide that says that, well, what we have to look at for a type of criteria when we're looking at this subspace is that completeness would be, okay, when we have this Cauchy sequence, we know since our space is complete, if we look at this embedding into C01, so we're looking at y inside of C01, side of C01. What we want is that a Cauchy sequence will converge somewhere. Since we're looking at this larger space, somewhere in C01. And all we need is for that, we know it does converge, and we know that there can't be another point it converges to. We need to make sure, though, that this point that we converge to has to be inside of y. So what does that say is that the limit of any sequence is contained in y. So in other words, in your complete space, a subset is complete if and only in the relative metric, if and only if it's closed in your original set. So that's the result we're going to try and use here. At least that's one framework I wanted to introduce within the scope of this question. And so here, intuitively, this seems to be closed because we have this greater than equal to. That's kind of the right reasoning, because we could say, first of all, you don't have to be approaching it necessarily this way. You could say, first of all, if we look at the interior points of y, we could say that if we use some nice epsilons, using a control over this the infinity metric, we would say, taking any function that's strictly above 5 in terms of its integral, a common trick is to use epsilon in terms of this value. In this case, we're dealing with the integral. We take away 5 because we know it's above it by some positive amount. So that's a common trick in these types of proofs. And what we can do is say, well, the integral of epsilon over this range is just epsilon. And so we're still above 5, should be above, if we do this comparison. And then we can also argue is by similar nature, if we look at a point in the complement, we want to show that what we can look at is y is open and y is closed. If yc is open, so there is reason to look at this. And another result Dennis likes to use a lot is that we could look at, well, y is the union of, so x for any set for any y. X is the union of the interior of y along with disjoint union, its boundary, disjoint union with its the interior of the complement. Okay. So what we're looking at here is that the interior of the complement is this set of functions that have evaluation less than 5. The interior of our set y itself is those that have evaluation greater than 5. So we are playing around with this a little bit more than you would need to within the scope of a question you may do, but just to get a feel for what we're doing. And just to point out some other revision that might be good to mention, since I haven't put it elsewhere in the slides. If y is equal to the interior of y and the boundary, what we said before, then y is closed. And so what we can look at is, well, we haven't classified fully the boundary yet, and we've only really shown that these types of points are on the interior of y, and the other way around is in the interior of the complement. But we can also argue that for the boundary, if you take any function there, then if you take, say, f minus epsilon over 2 or f plus epsilon over 2, then you can get to y or its complement. So it would be a boundary point. And so in particular, every element in y is either, every element in y is either in its interior or it's on its boundary, so it contains all its boundary points. And so this is a closed set, so a closed set in a complete metric space is complete itself. Okay. So I guess the important takeaway, the computation in this question isn't too difficult. I'm sure you're all comfortable with that. But for what we brought up from this, that is another important item to revise when dealing with these types of questions regarding open and closed sets, is this way of breaking up your space into the interiors of a set and its complement and its boundary. So for this one right here is disjoint union. Any questions thus far? Okay. Right, so we're getting to the last set of slides for this section. So for contraction mappings, that's the next one we're going to be looking at. For contraction mappings, this is motivating the fixed point theorem. The usefulness of this is gives us information about what happens to our function after we've applied, so information about the metric after we've applied our function. So it says that the distance between our functional evaluations is less than or equal to some constant, but the importance of this constant is saying that we have this fixed numerical value that we can use, and in the proof of the fixed point theorem, we use that algebraically. We have this inequality here. And what the fixed point theorem says is that in a complete matrix space, and this is important, there are some very maybe subtle and very important preconditions for this theorem. In a complete space, when you have a map from that space to itself, so from x to x, then which is specifically a contraction, then there is a unique fixed point. So what we often do in this course is restrict our if we have some sort of function that's nice enough, seems close enough to closed. So the reason why we talked about before, when we're dealing with a complete space, we take a closed set within that space. So that's a complete space as well. And we look at the function within that complete set, which is complete space, which is the closed set. And we do that such that restricted to that set of function is a contraction. An example is Picard-Lindoff, which we'll look at in a second, which is kind of the theorem we've been building up to this whole section of the course. So for this exam question, let's look at, for example, this interval 0.5, where this is an example of something we would do. We know that so let's ignore the fact that this is not a closed set, but let's just for now look at determining what we might try to do, which is in some cases see if we can restrict our function to get a contraction mapping. In this case, we're looking at the restriction of the function to f of x equals x squared on this set, on the regular metric from R, so the distance, the absolute value. So what we want is that f of x minus f of y to be less than or equal to c times x minus y, for c in 0.5. Sorry, not for c, for x and y in 0.5. And we want there exists some c in 0.1. 0.1. And remember, c can't strictly be 0. Yeah, remember one other important detail, c cannot be equal to 1. And so let's say this is true, then we're saying that then x squared minus y squared less than or equal to c times x minus 1. And what I might try to do is just say x is not equal to y for simplicity. Difference of two squares, algebraically, let's play around with this. I can make it like this. That's equal to c times x minus y. And then we're saying that x plus y is less than or equal to c. But this doesn't seem quite right because I could make x and y both quite close to c. In particular, I could make them quite close to 1/2. In particular, I could make them, for example, let's say what we want to do is drive some sort of contradiction. C. Let's take 1 plus c over 2. Let's think. Well, the way I write is x. You could say, if you want to do it a bit more algebraically, not knowing the direct answer yet, x and y are both 1/2 minus some small number. Your favorite small number is epsilon. And we want this in such a way that this 1 minus epsilon 1 plus epsilon 2. And we'll just make these both epsilon. We'll figure out what epsilon is later. Actually, no, I do want them to be different since we are assuming this was important. We want epsilon 1 to be different than epsilon 2. Please do keep that in mind. So maybe what we could do, let's say epsilon 1 is equal to 2 epsilon 2, for example. So now we're just dealing, let's just say that's epsilon. So we're saying 1 minus 3 epsilon. We want that to be greater than c for a contradiction. That's to say 1 minus c over 3 could be epsilon. Yeah, that could work. Okay, and that'll be a contradiction. And specifically, they use something very similar here. We've used something very similar here, where you could say the specific example could be these two, which still work in the same vein. The idea is you get closer and closer to 1/2 for each of x and y. So that's the example of showing something that's not a contraction mapping. And yeah, so we're going to look at this final theorem now, which comes with Lipschitz continuity, along with some example questions with it. So Lipschitz continuous, remember what that looks like. Specifically, when we're talking about the second variable only, we showed that it's Lipschitz, I should say, in the second variable. Lipschitz continuous is a stronger notion of continuous. Every function that is Lipschitz is also continuous, but in this case it's slightly different. What this says is that there's this bound we can make between the distance between a function, and we can directly connect that in a very good important way through the distance between our input. In this case, the second variable is specifying the second input. And the way that we can use that is from the basically mean value theorem, the analog of the mean value theorem to two variables. Says that when we're dealing with a closed interval, so a compact set, AB compact, if a function is differentiable in AB, then you can apply the mean value theorem to say that the derivative is bounded. And so if the derivative is bounded, then you have Lipschitz continuity. Yeah, so because this K then lends itself to this K. So you use, what you typically do is you work in a space of functions, say where the, you're dealing with, say, the set of bounded functions in, say, C1, or just any space you have bounded derivative, which is very common to work with. Then you have your function has this Lipschitz continuity property. So for example, if you say have a function that is C1, so it has continuous first derivative, then if I say the min-max theorem, you know that the function itself anyway has this bounded derivative. And so again, you could apply that here to get Lipschitz continuous. But in any case, what we use from that is that it applies as one part of the proof of Picard-Lindorff, which is a good proof to know. It's very nice. It's really, I feel like the proof is using all the properties that you need, of course, for what the fixed point theorem says, your completeness and so forth, and applying it all to get a lot of its conditions. So that's a good proof to know. But what it says is if your function is Lipschitz continuous, your g, and you're solving a differential equation of this form, then when you rearrange this as an integral equation and you use that as your function you're trying to get a fixed point from, you get this unique solution around A. Okay, so you apply it to a particular space X, which is a closed subset of R2, and you say that in that space there is this unique solution, because you say that unique solution is the unique function that is this fixed point. Okay. So yeah, an example of using that is the last example I'll be walking through is this one here. So how does this work? We'll kind of mimic it a certain way. The proof of this, so the way that we do this is we say that, okay, y would then be 4 plus n equals 0 to, so what are we looking at? Well, yeah, y is a function of x, so we want y of x to be n equal 4 plus 0 to x of, let's say, e to the negative t times y. We're looking for this, dt. So what we could look for is say this is our transform of y. We want fixed point. We want the fixed point of t. That's what we're looking for. If we can do that, we can obtain our y. And so the way that we have to approach this is the Picard-Lindorff does, if you look through the conditions of Picard-Lindorff, it does give you the solution. But if you want to be a bit more specific in working with how you actually find where that solution exists, let's walk through that. I believe we have that on the slides. In particular, if you find the partial derivative with respect to y, you get this continuous function because everything here is an elementary function. So we do want to, first of all, give a bound on the interval domain that we're dealing with to get a continuous function in terms of x and y. In this case, yeah, we'll go through the full rigorous details. In this case, you can use -1 to 1, and you can look at the maximum value of the maximum absolute value, right? Where you could say that in this interval, it's bounded by, say, 1. So x e to the negative xy, bounded by 1 on -1 to 1. And you'd follow from, yeah, that seems correct. Actually, no, that's not correct. Because you could have negative values, could be bounded by e to the. You would have to restrict your function around 4 as well. Sorry. But yeah, you are dealing with x around 0. Let's say we deal with y around. You're dealing with y around 4. You get some sort of bound here. Let's say y is between. We'd have to make it small enough. Let's say. What can we do? Let's say. Well, actually, I can't really say definitively. In the test, you will be most likely given the more precise form of Picard-Lindoff. We can, because there is a specific way we remember that we have to do this in order for everything to work out with the whole contraction and everything. Maybe I'll just leave that here though. I'll just write well, yeah, y is going to be, I'll show you what it looks like. Y is 4 minus epsilon, 4 plus epsilon, some k, which is say, you could say k is the maximum value of, which is equal to say e to the maximum could be, for instance, e to the negative, or positive, sorry, 4 plus epsilon. So you're bound. You know that then you're bounded by 4 plus epsilon for any choice of epsilon. That's fine. The other details you have to work through is finding this epsilon such that this restriction, in this restriction, you're going from t from y t maps from x to x. So you want to make sure that the codomain x would be the set of functions, set of y from r squared to r. So r to r. I should say. Yeah, in this case, we wanted 4 minus epsilon, 4 plus epsilon. And our input, yeah, we are also restricting to -1 to 1. So we have this closed interval AB. And what are we doing from there? We want to make sure that the absolute value of ty, we want this to be in the same interval of 4 minus epsilon to epsilon for us to be contained still with an x. So when we map t, we still get an element in y. So that's to say ty minus 4, what we want for this, which is this integral 0 to x ty dt. Well, this is less than or equal to k times x. It's less than or equal to k. Okay. That's fine. And so we would want to then choose k such that this holds. We would want then epsilon less than or equal to k. So k is less than or equal to epsilon. And we would also want that this other result. So I may have to review this later, but that's roughly where we're going with this. But I'll hand it over to Jeff now for the next section. And we'll continue on that.
Oh, she's not here.
Sure.
Okay, so
now we're going to move on to chapter 3. So this is basically like an application of all the metric spaces stuff, but now we're treating it in terms of like functional spaces. So you've already probably seen like C01 before, but now I guess we're going to look at like some other examples. So the main thing we care about is like, I guess, convergence of sequences of functions. So one type of convergence that we're going to be looking at is pointwise convergence. So the formal definition is basically saying that the limit as n approaches infinity of fn of x, where I just choose some x in the set x here, is going to be some function f of x. So basically all we're looking at is that the function values converge to some like other function value. It's just looking at the sequence of function values rather than the function as a whole. So what I mean by looking at the function as a whole is basically uniform convergence, right? So uniform convergence is basically saying the function approaches another function. Formally, we're looking at basically if I can find some n such that there's some like k of epsilon, which only depends on epsilon, then whenever n's bigger than that, we're within epsilon distance for all x. So in the previous example for pointwise convergence, we can pick our k in terms of x, but for uniform convergence, it's a bit stronger. So we have to pick purely based on epsilon. And an equivalent like definition for uniform convergence is that we'll just take the supremum of that difference over x, and that has to be less than epsilon whenever n is bigger than some k. So we can just look at the d infinity metric instead. So it might be a bit like tricky to like, I guess differentiate between pointwise and uniform convergence. So what we already know is that it's quite clear that if you have a uniformly convergent function, then it's automatically going to be pointwise convergent to whatever the limit is. But on the contrary, if you go the other way around, pointwise convergence doesn't necessarily imply that the limit is going to be uniformly convergent. So a simple example is if we have this function fn of x, where it's our favorite number whenever x is equal to n, and then zero elsewhere. So it would look something like this is n, and then this would be our favorite number. So we should say this is 0, and then it's 0 elsewhere. So if you look at the limit of the function values, so I just pick any x I want, and then I plug it into the function fn, then clearly it's going to be 0 as n approaches infinity, because if I just pick n to be greater than x, then fn of x is just going to be 0. But if we look at the supremum of fn minus 0, or like the d infinity metric between fn and 0, then it's always going to be our favorite number, 67. So if we pick epsilon to be less than 67, then we don't have uniform convergence, basically. So at least to 0. So here's some like useful like things that you can use. I think I'm going to prove some of them later on. But basically, if we have pointwise convergence for some function fn to some other function f, and we have some continuous function g, then we can basically exchange the order of the limits. So we can bring the limit inside. So that's hopefully something you might have seen before, but now like this is us basically formalizing it. So here's a little proof. So since we have that the pointwise limit is f of x, then by definition there exists some n of epsilon, such that whenever k is greater than n, then we have that the pointwise difference between fk and f is less than epsilon. So if we use continuity of g, then whenever we have basically our input values are within epsilon distance, where we choose delta to be epsilon, then we can have that our G value here is going to be within an epsilon naught distance of G of f of x. And then so that basically shows that the limit is equal to that.
The positive integer p is that type of thing.
Sorry?
The then false positive integer p. Is that relevant?
For all positive integers.
Oh yeah, let's do a typo.
Yeah.
Yeah, sorry about that. Oh yeah, another one is if we have a Cauchy sequence in terms of the infinity, then if we do pick some like x in a to b, then the sequence of the function values is also a Cauchy sequence in R under just the regular absolute value. So this was used in that one question from the shortlist, but this is like a simple proof of it. So if it's Cauchy on the infinity, then there exists n and m such that whenever n and m are greater than some like k epsilon, then we have that the infinity between the two functions less than epsilon. So that's just the definition of it being Cauchy. But since we're looking at the supremum, we know that if we just pick any sort of like x value inside this interval, it's automatically going to be less than or equal to the supremum. So we can bound this by epsilon. And then this is basically the same as the condition for being Cauchy in R, because these are just going to be like numbers in R. So this is another like thing that you might have seen before. So previously, if you've done like complex analysis or like even I think MATH3611, there might be some times where like you want to swap the limits inside the integral, but it's always a bit hand wavy on why you can do that. But now we know that well, if you have uniform convergence, then you are allowed to basically interchange the order of integration and limits. And that's basically what uniform convergence theorem is. So it's a nice proof for it. Basically, if we pick n large enough and we consider the difference between the two integrals by linearity of the integrals, we have that this left term is equal to that. And then we use the inequality that the absolute value of the integral was always less than or equal to the integral of the absolute value of the inside to go from this line to this line. And then obviously that's going to be bounded by the supremum of that function. And if you evaluate it, since this is just going to be some constant, then it's going to be b minus a times the inf norm, which is going to be less than epsilon if we choose our n to be greater than this n here. And then that basically shows here that the limit holds. So aside from obviously C, like on some interval like a, b, we also have LP spaces, which is kind of similar to the LP spaces of like sequences. So this is capital L now instead of lowercase l. And then the way we define it is similarly, we have some sort of like P norm, which in this case is going to be the P fruit of the integral from a to b of f of x to the p absolute value. So we can define capital LP space as the space of functions where the P norm of that function is going to be less than infinity. So similar to how we defined it in sequence space. And then now we have a notion of convergence in LP spaces, which is basically saying the, well, if we treat it as like an induced metric, then the distance goes to 0. Or the LP norm of Fn minus f is going to tend towards 0 as n approaches infinity. So here's a pretty useful identity. So basically we can bound any p norm by the infinity norm. So if we have uniform convergence, then we're going to have convergence in LP, basically. So that's one use of that. And then this is quite simple to show as well, because we have the LP norm. It's going to be A to B of fx p dp, sorry, not dp, dx. And that's going to be less than or equal to, if I plug in the supremum of this, so it'd be the nth norm of f p x 1 over p, and then this is going to be b minus a times nth norm to the p, or to the 1 over p, and then we just get the result here. So another identity, which is like, I believe it's assumed, I could be wrong, but it's Holder's inequality, but now for integrals. So basically, instead of doing Holder's inequality over like sums, now we just replace the sums with integrals, and then the terms in like sequences with functions. And of course, we still have the condition that P and Q are going to be Holder conjugates. So here's an example of an application of Holder's inequality. So this is one of the shortlist questions. It's basically saying, well, if I have convergence in LP, then I have convergence in LQ whenever Q is less than P or equal to P. So if we choose these very, I would say unnatural, but like they work, these two conjugates, P over Q and P over Q minus Q, then we can use Holder's inequality on the left-hand side here, which is going to be less than or equal to b minus a to the p minus q over p. And this would be the integral from a to b of this term here to the power of q over p. And then if you, take the qth root on both sides, then you would get that the Q norm of difference is less than or equal to b minus a to some power times the P norm of the difference. So by some pinching argument, you can say that, since this is bounded by 0, if this approaches 0, which is convergence in the LP sense, then this is also going to go to 0 by pinching argument. And then that shows convergence in LQ. So another thing that's also like quite, important in this chapter is basically convergence of like series, so like sums. So this is like a result that I believe you might have seen in first year. It's basically, checking that if I have a series that's absolutely convergent, then I get convergence for free. So it simplifies a lot of things. So for example, if you check the convergence of, say, minus 1 over 2 to the n, then you can just check the absolute convergence, which is going to be 1 over 2 to the n, and then we know that's going to converge because it's the geometric series. But obviously that's quite a simple example. There's some more like non-trivial ones. And then we can also generalize this notion to like any sort of like finite space, right? So all we have to check to see if this sequence, the sum of xn, where xn are just going to be your vectors in your Banach space. To check convergence for that, all we have to do is check convergence for the sum of the norms instead. So it's kind of like an extension of the previous idea, but now instead of using only the absolute value, we're using the norm space. And then a corollary of that is the Weierstrass M-test. So the way it follows from the previous theorem is basically, if I have this function and it's bounded by this, then the sum of fn, if you want to check if that converges, we check it if it absolutely converges. And then that's going to be bounded by the sum of mn. So all we have to do is check if this sum on the right-hand side converges, basically. That's the intuition behind it. And then that's the test. So if we check that this sequence converges, then Fn, well, the sum of Fn is going to converge in X. It also converges uniformly, but there's a few steps to proving that that's also true as well. But the general intuition is basically this. It's just another form of comparison tests. So I guess putting some of it together, we have another shortlist question. So let's just say that the sequence Fn converges to F on AB, and obviously Fn is going to be differentiable. And we also assume that the sequence Fn dash converges uniformly to some function g. Then what we want to show is that F is also differentiable in AB, and that Fn dash converges uniformly to F dash, or basically F dash is equal to G. So first we use the fundamental theorem of calculus to basically rewrite this difference here as an integral. And then we can apply the limit as n approaches infinity to both sides. So lim n to infinity, lim n to infinity. Yeah. And then by uniform convergence theorem, since Fn dash converges uniformly to G, we can bring the limit inside. And then obviously on the the left-hand side, we're going to have Fn converging to F. So we get this result here. And then now we can differentiate both sides with respect to X. And then the fundamental theorem of calculus tells us that F dash is equal to G of X. And since X is arbitrary in some interval AB, then we basically get that F dash is equal to G. Okay. And then the last little bit of this chapter focuses pretty much on just power series. So little definition beforehand. If we have some power series, sum of an x to the n, then we have this number here that we can track called the Cauchy-Hadamard parameter, which is the lim sub as n approaches infinity of absolute value an nth root. So this is kind of like the, root test that you might have seen in first year. And then if you don't know what lim sub means, because it's separate from limit of the supremum, it's basically saying if I take the supremum for k greater than or equal to n, and then I take the limit as n approaches infinity. So you can think of it as sort of the supremum of all the tail elements. If I have this as a sequence a1, an, you can think of this value as sort of the supremum here, where n is going to be large. So this is the Cauchy-Hadamard theorem. It's pretty similar to the, I believe, the root test. And it's also a shortlist question. So basically what it states is if I have a power series and I have my Cauchy-Hadamard parameter, then the power series converges whenever b times the modulus of x is less than 1, and it diverges if it's greater than 1. So let's walk through a proof of it. And if we set r to be 1 over b, then we could call r the radius of convergence, because we know that the series is going to converge whenever absolute value of x is less than r. So we can think of it as if I'm within r's distance 0, it's going to converge here. So from using the first little facts from the start of the series part, all we need to check really is that the series converges absolutely. Now, if we use the definition of what the lim sub is, we basically know that eventually there's going to be some n such that this is going to be less than b plus epsilon, where we choose some arbitrary epsilon whenever n is greater than or equal to big N. So what this is basically saying is, well, the absolute value of this nth root minus b less than epsilon, which is basically the limit part of it, and then be the supremum of that. So like this is going to be less than or equal to the supremum of that whenever like n is greater than n. Oh my god, what's going on? 1 over n, and that's going to be less than b plus epsilon, or some like n basically. And now, since we know that b times the absolute value of x is less than 1, by properties of real numbers, we can pick some number q between those two values. And then we choose our epsilon to be q over the absolute value of x minus b, which we know is going to be greater than 0 by this inequality here. So if we choose n to be sufficiently large, then necessarily we're going to have that the absolute value of a n nth root times the absolute value of x is going to be less than 1, and it's also going to be less than q. So what we can do is that if you expand the series out, you can expand it out to the n minus 1th term here, and then the nth term and beyond here. So this is basically like, as I was saying before, like the tail elements. So this is a finite sum, so we know it's going to converge. And then now this is going to be less, the right-hand side sum is going to be less than this geometric series here. But since we know that q is less than 1, then we know that the series is going to converge. And it's going to converge to q to the n over 1 minus q. And since these are both just like finite numbers, we know that the series is going to converge absolutely. And so because it converges absolutely by the theorem at the start, we know that it's going to converge in general. Last bit of this chapter, basically it's a result that follows from everything we've proved so far in the rest of the chapter. So it's basically just saying I can differentiate power series term by term. And that might have also been something that you've seen in first year. But now we actually have the tools to prove that we can do this legitimately without just like hand waving it. So do you want to take a break now or later?
Take a break now.
Yeah.
So what we'll do is take a break now. Unfortunately, we haven't gotten the chance to order the pizza yet, so we'll also do that now. Please do take the chance to get some water, stretch your legs and everything.
Just turn your screen off.
But like always being established is like key in that version. Like you need to go for a lot of examples. We don't do that. Actually. Yeah.
Okay.
So
We should be back now.
Alright.
Okay.
I was about this cycle actually. And the finals
So for those of you joining us online, we should have the stream continuing now. Jeff will be picking up in the next chapter. So we're moving on to topological spaces. For those in person who've ordered pizza, will be here in about 30 minutes. We'll have that. I guess we'll have a break before the last hour of the session, so we still have a bit to go.
You have to unfreeze it on the
Yeah, so I'll unfreeze on the screen. So we get started.
All right, so now onto topological spaces. So, what is a topology? It's this is the example that comes up when you Google topology, but unfortunately, we're not doing this yet. What we're doing in this course is point set topology, basically. So what we're dealing with is like basically open sets, like what makes a set open, and like what are the properties of open sets, and like how can we use that to do like cool things, right? So if we have a non-empty set X, then we can define a topology on X to be some sort of like subset of the power set of X, or just a collection of sets, where these sets have the following properties. So X and the empty set are both in the topology. So we typically use tau to denote the topology on subset. And the union of any number of sets, even infinite, in this topology is also going to be a set that's in the topology. And now the finite intersection of any two sets is in the topology. But for infinite intersections, it doesn't necessarily have to hold. So we call X and tau, the pair, a topological space. And then now we define the sets in tau to be called open sets. So if you remember from like metric spaces, like these two are like properties of open sets. So union and like countable intersection. Now we don't need the notion of like a metric or like distance anymore. All we have are like these open sets with these properties. So it's kind of like, I guess, an extension of that, but now we remove the need to have like a metric. So it's even more general than like all the other like spaces we've like looked at so far. So these are like the main sort of examples that you're going to come across. Our favorite discrete topology, which is just every single like a power set of X. The coarse topology, which is just the empty set and X. The metric topology, which is basically the open sets from the metric space, like XD. So this is like what you might have seen before, where your open sets are just the sets where you can find a ball, like an open ball inside around some element. And the cofinite topology, so it's a set of sets where each set, so X minus some set U is going to be finite. And then the co-countable topology, which is kind of like an extension of that, but now instead of U being finite, X minus U being finite, it's also, it doesn't have to be finite, but it just has to be countable. And then the subspace topology is basically kind of like the sub-topology in a sense. So it's kind of like the topology that we get if we restrict the topology to some subset. And the way we formally define it is by taking the intersections of the subset and sets in the normal topology, X and tau. And you can check that this also forms a topology. And usually if you are going to prove something, or like trying to disprove something, two easiest examples to use, discrete topology and coarse topology, because they're often very annoying and disprove a lot of things. So, but this is like mainly talking about like open sets, but now we have like a notion of closed sets as well. So without needing a metric, we can define a closed set to be the complement of a open set. And the set of closed sets also form, well, doesn't form a topology, but basically we have these similar like sort of properties, but now we kind of invert all of the, I guess, intersections and unions. So now we still have the empty set and the whole set X being in this collection, but now instead of being any arbitrary number of unions, now it's any arbitrary number of intersections, and instead of finite number of intersections, now it's finite number of unions. And it's fairly easy to see why this holds if you look at De Morgan's laws. So we just take the complements of both sides, basically. So now onto neighborhoods. So an open neighborhood is just an open set in the topology that contains some element that you want to be the neighborhood of. And then even more generally than that, just a regular neighborhood is a set that contains an open neighborhood. And we can write the collection of neighborhoods of some element X as NBHDX. And now we have a notion of like the interior of a set, which we can basically say is all the elements in that set where we can find a neighborhood around it that's a complete subset or equal to the whole set Y. So what we're basically doing here is replacing the need for open balls with open neighborhoods so that we don't need a metric anymore to sort of define these properties. Yeah, so using our previous definition for the interior, we can define the boundary to be x minus the union of the interior of y and its complement, and also its closure of y to be the union of its interior and its boundary. So similar to what we've seen in metric spaces, but now, of course, we've defined the interior to be in terms of open sets rather than necessarily open balls. So following from that, we have a notion of convergence. And this is basically the same as what I was saying before. So now we replace an open ball with an open neighborhood, or just any neighborhood. And formally, we say that a sequence converges to some value x if for every neighborhood of x, we can find some index such that eventually the sequence is fully inside of that neighborhood for all n greater than this value k. So here's an example of, like, I guess, putting that definition to use. So this is the shortlist question from week 7. So we're given the cofinite topology, but now we're gonna do it on n. So replace x with n. And then we want to find and, like, I guess, categorize whether or not these sequences are convergent or not with respect to the cofinite topology. So before we think about if they even converge or not, we should probably think about what the neighborhoods of, like, some point x is. Since we're looking at the cofinite topology, you can kind of see how it's equivalent to the set of these sets where V is some finite set, or basically n minus some finite, like, subset of n. So for example, a neighborhood of, like, 2 could be like n minus 1, 3 with respect to this topology. So for the first part, we want to find all the limits of the sequence n. So like 1, 2, 3, all the way to infinity. Or we want to show that no limit exists. And what we claim is that this sequence converges to whatever value we want. It converges to everything. And the way we prove it is by considering neighborhood of any element, say x in n. And let's just suppose that V is any element in the neighborhood of this, like any neighborhood of x. Then we know from the definition of the cofinite topology that x minus V is a finite set. So we can write the difference as some, like, set in some order A1 to AK. So then we can write V as the difference between x and this finite set. And let's just say that AK is the maximum element of the set as well, without loss of generality. Then if we pick our, like, K of V to be AK plus 1, then we're going to have AK plus 1 and everything beyond it being a subset of our V. And so that means that our sequence is eventually going to be in this part because it's going to be increasing. And it's eventually going to hit the set. And then once it hits the set, it's always going to remain in the set. So we know that it's going to converge within that neighborhood. And since this neighborhood is like any neighborhood of any element, then it just converges to anything. Now, what about this sequence here? So it'd be 1 plus minus 1 to the n. So it'd be like 0, 2, 0, 2, or 2, 0, depending on where you start. Does this one have a limit or does it not? Let's find out. So we claim that no limit exists. And here's a little proof. So let's just say it converges to 0. Then we pick some neighborhood, let's just say n minus 2. So it'd be like, say 0, 1, 3, all the way infinity, but we don't have 2. And that's obviously a neighborhood of 0. So if we assume that it converges, we can pick some k such that, let's just say n is greater than k, then this, which is equal to 0, is going to be in that neighborhood. But then n plus 1 is going to be 2, which is not in that neighborhood. So that's a contradiction. It can't converge. And then by similar logic, you can also show that it doesn't converge to anything else. But you can replace 2 with like 2 and 0 here with like, you can kind of swap them and replace them with something else. And then now for like the overall like categorization of these convergent sequences, what we claim is that the sequences are eventually constant, or they only repeat a value a finite number of times. So for example, like, let's just say it could be a monotonically increasing or monotonically decreasing sequence, or it could be like a sequence that only repeats, like say, well, it doesn't repeat any values an infinite number of times. So you could say like, I don't know. It's like, I guess an easy example is the monotonically increasing or decreasing sequences. So let's just prove that if it is eventually constant, then it is convergent. So let's just say it's eventually constant at some value x, and we take v to be some neighborhood of x. Then let's just say there's some index that every term in the sequence after that index is going to be constant at x. Then that's what we can choose our k of v to be. Because, of course, any an where n is greater than k of v is going to be equal to x, which is obviously in a neighborhood of x. So it's going to be convergent. Now let's just say it only repeats values a finite number of times. So no value, say like 1 or 2 is like repeated an infinite number of times. Then following from like our previous argument, we can write an open neighborhood of any value as the difference between n and a finite set of values. Now, since an repeats values in the sequence only a finite number of times, eventually we can find some index such that it doesn't hit any of these values here. So then that means our sequence is going to be fully inside this neighborhood because it's not going to hit any of the things that it excludes. So, and since we can pick neighborhood to be anything, we know that it's going to be able to converge to anything. And now just to close it off, let's just suppose that it repeats a value an infinite number of times. Let's just say like some value x. Then we can just take a neighborhood that includes that x. But like, sorry, if it excludes that value, because you're always going to hit that value again, no matter like what index you pick. So for example, let's just say it repeats like x an infinite number of times. Then we can pick like, say, x minus x. And no matter what index I pick, I'm always going to hit x eventually, which means I won't be in the neighborhood. Whenever I have well, this would be one example of a neighborhood where it doesn't converge. So all you need to show that a sequence doesn't converge is that you can find one neighborhood where you can't have that index where it's always inside. So now into continuity, I'll hand it over to Daniel.
Oh, wait, can I just I don't use that one. Yeah. I don't really like holding stuff.
All right.
Should I just sure?
Do you want me to get the new slides?
Oh yeah, probably yeah.
Just give us for a second. So we're back on the stream. Just tapping this time. Just about to get started. We just had to update the slides. Oops. There we go. And we wanted slide 77. Just take a while to load. So yeah, same as last time, I think. So the style is definitely should be good.
Yeah.
For 77.
Yeah, it's fine.
Continuity, yeah.
Yeah.
Oh, you see all the, can you just scroll?
Wait, what about this? Should I put that in?
Oh, yeah.
So
We're getting started back now.
yeah, okay, so okay, going back. Yeah.
So we'll be here soon.
Yeah, so we'll probably have a break very quickly. But yeah, before we have a break, yeah. So like we need to define what like continuity is for like a general topological space, right? So like a general rule of thumb is just if you forget your definitions about topological spaces, just go back to your metric spaces and always just think about what it is in terms of your open sets. So like on metric spaces, we said that like Brendan showed that a function was continuous if the preimage of each open set like was also an open set, right? Like if you notice, you don't really need anything about the metric space to actually give that definition. So the generalized definition actually, you can just clearly just define it as function f between two topological spaces is continuous if for every, I guess, open set here, U, we have that the preimage of that open set is also open. Okay. So this is like a pretty stupid question, but it's self-explanatory. Just to like drive it home. If you have two topological spaces, f is continuous, which of the following statements say which of the following statements must be true? This is literally just a definition, so the second one obviously has to be true. But then the first one, that doesn't necessarily have to be true. Okay, so you see how like this one is saying like if we start with an open set in, I guess, the domain, is the image of it also going to be open? We can give like a pretty dumb example, something like, let's say we just choose like, dude. Okay. Let's say we just do a function from the real numbers to real numbers. If I don't specify anything about the real numbers, it's just going to be the usual topology. Let's say we send everything just to 0. So like it's just going to be the constant function where we send to 0, right? Clearly this is continuous because like if you just think of any open set, if it contains 0, like if we just start with the open set, if 0 is in the open set, then clearly the preimage should be this. If 0 is not in it, the preimage will be empty. Both of these are obviously open, right? Sorry. But like as you can see here, like what can we do? If we think about the open set R from the domain, taking like f of R, we just get 0, right? Like the point 0, which is not open, right? So one thing that I wanted to mention with this is that continuity does not tell you information about the image, but if we have a condition that we're going to talk about later called compactness, it will actually be strong enough. It should be reminiscent in your like metric spaces. Like metric spaces is you use the condition of compactness there. Okay, so house of topological spaces. Yeah, so like we're just basically trying to we're sort of translating everything that we wanted in metric spaces in a generalized form, right? So like we were able to we kind of essentially thought of closeness using the neighborhoods definition, right? So like every to capture like when we're getting closer and closer, we would say like, oh, it must be in an open neighborhood containing that point, right? But we don't really have a notion of farness, I guess. So like what does it mean for 2 points to be certainly far, or how do we tell like they are actually far away, right? Key thing is that topological spaces, we only have the information of open sets, right? So to say that we want to have 2 points be far away, we have to describe it using open sets. And if you think about it in like the metric space example, like if you think about it in the metric space example, like you have 2 points X and R, and they are far away, right? Like another way of saying that is like you could just draw open balls around X, open balls around Y, such that they don't intersect each other, right? Like if they are far away enough for that, then we can construct some sort of open balls or open sets, right? We're basically just going to imitate that definition into Hausdorff topological spaces. So this is saying, like if you read it, it's just saying that X as a topological space is Hausdorff if for all X and Y in X, such that X is not equal to Y. We can find some sort of open sets U and V, such that X is in U, Y is in V, but their intersection is empty. Okay, so like it's like the same picture. I always like to use the pictures that we had with our intuition of metric spaces. They're not always true, but like you get a certain sense of which ones like have the same like visual picture. So like this is what you say is Hausdorff. You can find some sort of open sets around X and Y such that their intersection is empty. Okay? And a key thing of why this is important is because, like, as it's written there, if a topological space is Hausdorff, your limits of sequences on the space behave nicely. So what we mean by that is like, I'm pretty sure we saw an example just then with the cofinite topology. The cofinite topology is not Hausdorff, and we saw that the limits of certain things behaved quite weirdly. Like if we scroll back, like part 1 was like the n can converge to anything, right? Like that shouldn't really be what we want. If you think about like if you want a nice behaving kind of space, we don't really want that, right? But if we do have Hausdorff condition, then what it means is like if we have a sequence xn, right, of points that like I guess converge to x, but we also have that converge to y, we can actually prove that these 2 points coincide. To give a proof, yeah, let's try and give a quick proof. If we say like xn converges to x, xn converges to y, we could say that so for like proof of contradiction, let's say like we want to prove x is y, right? Proof of contradiction, let's say x is not y. Right? So if x is not y, then by like above, by the Hausdorff condition, we can find open sets U and V such that their intersection is empty, right? So we'll take the same letters, by the way. I'm just not bothered to write them. We found the open sets U and V. And by the definition of the fact that they, I guess, converge, we can set like the open set U, and we know we'll have some sort of constant n, right? Such that for all n bigger than this n, xn is like going to be inside U, right? Similarly, come on, this is just like definition slop. For there is a sort of m such that like little m, we have like xm is also in V, right? Then like you clearly see the example. This condition is like where it's above, so you just choose like, let's just say we choose L as like the bigger one of the two, right? Max of n and m. Sorry, I'm not used to using this. Yeah, we choose L to be the max of n and m. Then, like XL would be in U, but it's also in V, right? So it's like, you know, like, yeah, like it's in the intersection. But come on, that's contradiction, right? Because we said that the intersection was empty. Okay. Yeah, so that's like a quick proof. Yes, we get another quick proof. So this is like a 2018 question 8 example. It says that if we have XB topological, it's Hausdorff. we have a continuous injective function, right? We want to prove that X is a Hausdorff space as well, right? So, like these ones, you just kind of naturally go with what definitions you need to use, and you'll get the proof. Like, if we prove that X is a Hausdorff space, we want to show that for any like X and Y and X, right? We want to show for any X and Y and X, we can find open sets such that they don't intersect, but they contain X and Y, right? So, we can't find it right now. But let's say we move into X dash, because we know X dash is Hausdorff, right? So f of x and f of, like, we will obviously assume that these aren't the same. So that was one of the parts of showing for Hausdorff. Because it's injective, right? We know that f of x is clearly not equal to f of y, right? So f of x is not equal to f of y, which means since x dash is Hausdorff, right? X dash is Hausdorff, we can find some sort of open set like U, with f of x in it, f of y in V, and like U intersect V is empty, right? Then, like, what do you think? Like, if we have U, which are open sets in X dash, we take the pre-image, right? So if we take the pre-image of U is also open because it's continuous. The pre-image of V is also open, and this has nothing to do with continuity. It's just like pre-images, like you can just confirm pre-images will do this. The pre-image of empty will obviously be empty, right? So intersection will be empty as well. So we have open sets F inverse U, F inverse V, and clearly X is inside F inverse U because F of X is U, like inside U. And Y is inside F inverse V, right?
Why is the pre-image of them so?
Y is the pre-image of empty set empty? Sure. So that's not what I was saying. Like, what I was saying was, like, you can prove this quite easily from the fact that this is true. Like, if you assumed that this, like, if you assumed like there was something inside here, right? Like A is inside the intersection of these two, right?
Yeah.
Then you're saying that A is in the, A is in F of inverse of U, A is in F of inverse of V.
Yeah.
So like, that's just what I was saying.
Good on.
Yeah, like, I mean, like, if the
back in security.
I mean, yeah, also, like, the pre-image of an empty set should be obviously empty, because, like, if there was something in there, you just take F of A, and, like, that's not empty, right? Like, you get what I'm saying? Yeah. So, yeah. I mean, yeah, this is easy check. That's what I was saying. Yeah, and so we're done, right? That gives us our open sets for, like, X and Y, which is arbitrary. So we're done. That makes sense? Yeah. So, yeah. Yeah, I guess we'll go through this. So I think a key thing to also notice while you're doing like open sets is that, like, you can describe open sets in like multiple ways, right? So, like, if we take something that we're used to, right, which is R with like the usual metric topology, then like the open sets that we're obviously very used to because of the metric topology is like an open interval, right? But like there's also something which is open, which is of this form, right? I will just make you guys confirm that this is an open set, right? But like, this isn't really that much different from what we are used to, right? You just like union a bunch of open intervals to get this, right? So like, that is basically just the key idea. Like, if we already have some minimal amount of things which if you union it and you can get the other things, we don't really care about the other ones to describe the topology, right? So we call that a base. When we say a base for topology, right, is a subset of the elements of the topology, such that every open set can be expressed as a union. So, yeah, it's like following the key example that we just did. The open intervals form a basis for R. Yeah. Yeah, I won't prove it. Like, it's pretty obvious. Like, you can try and prove it. But with the metric topology, by the way. Yeah. But we also have a notion of base at a point. I don't know if this guy's used quite a lot. Do you guys use this quite a lot in your like problem sheets, like the local base ones? yeah, but like you can just think of this as like a localization of the notion of a base. So instead of looking at the entire space, you really care about the open sets that only contain a certain point. It's like there's like this two views of either looking at it globally or looking at it locally, and I guess this is like the local definition of what you mean to look at a base. I guess one thing I will notice is like, if I just read the definition, it's like if you have a topological space and a point X, a local base is like another subset of the open sets, right? Subset of the topology, which all include X. And if you have any open set including X, we must have some smaller open set including X inside the local base, right? So this is a bit different to the fact that a base, we wanted the unions of it to form the other open set. This one is just you have to include it. If I try and explain why this is a correct definition, like I can't really right now, but like it has to do with something called like filters. And this condition is enough to do what we really care about. We only really care about local bases as like a poset, is what I'll say. That doesn't really mean anything to you guys, so I shouldn't have said that. Yeah. And then this one's a really good characterization of bases. So like this is an intuition of bases, but like we like really do think about like a base for topology as like the smallest kind of, like as I said, we stripped away the ones that like we stripped away these ones like when we're describing it, because we already know these can be formed from the intervals, right? So a base, if you really want to think about it intuitively, it's like you're having like the minimal number of information, like the minimal number of pieces to form your topology through unions, right? But if you follow like these two properties, you can notice that like you should have that those elements in the base covers all of X, right? Because of X is already an open set of itself, right? X is an open set of itself. But the base should also be as small as possible in the sense that like if you have some sort of X in V1, like the intersection of V1 and V2, for V1 and V2 in like the base, I guess, we can find some other open set V like in B such that X is in V. Like it's like if you can't do that, then you wouldn't be able to express, I guess, the open set that was made using V1 intersect V2, right? So another, like it isn't another characterization, but like there's a way to form another topology using this sort of I guess operation. So if you have an X as a set, and let's say we take some sort of like basis, like candidate basis, it's not a basis, but a candidate basis from the power set of X. So it's a collection of subsets of X. Then we can say that this tau, so this tau, I can't say it's a topology yet. Tau, where V is a union of sets in B, it's a topology if and only if what we've said about those two things are true. So the union of V and B for all V is X. So otherwise, like we like to say B covers X. Or for every other V1 and V2 in B, and like if we have some sort of X in V1 and V2, we have some sort of V, like right? We have some sort of like smaller V that we want to be included in B. If this property holds for B, then the tau that we made, it will be a topology, and the B that we have will actually be a base for that topology. Okay, does that make sense? So, yeah, like notice that notice the sequence of things you're doing. Like you're choosing a B, you're checking that these two things are true. If these two things are true, then the tau that we define here is a topology, is the kind of sequence that you're supposed to take. I think it's also true that this tau is actually unique in the way, like, if these two properties are true using the base, and you make the tau just a topology, right? If this B also acts as a base for another topology, I'm pretty sure that topology is supposed to be unique, as in it is supposed to be, these two topologies are supposed to coincide. But I guess you can read that on your own. How will we apply this criterion? 2022 Q6. obviously we'll skip the definition of a base, but it says like consider the set G, right, which consists of the empty set, the collection of all open rectangles in the plane. So something that looks like this, right? And then the question says prove that G is a base for topology on R squared. I mean, there's multiple ways to do this, but the first thing to notice is that it says is a base for topology. So we don't actually, it doesn't specify which topology. So we can actually use the criterion above. So if we show that G satisfies these two things, 1 and 2, right, then we know there exists some sort of topology tau, which B will be a base for. Okay, and so that's probably good enough for us, right? So if we try that, so first criterion, we want to show that it covers X, right? This is a classic technique, by the way. Like if to show something has an open covering, you can just go to each point and find an open set including that point. If you do that, the unions of those open sets become a covering. So like what I mean by this is like, so to show it satisfies 1 first, like notice for notice for all points X and Y. In R squared, we can clearly form like a rectangle, which, you know, like if this is X and Y, right? We can just form a rectangle where we like plus minus 1, right? So like, we'll say it's like X minus 1, Y minus 1 times X plus 1, Y plus 1. That makes sense, right? Oh wait. No. It should be. Oops, my bad. This is right? Yeah. So like that's the rectangle that we were like. That's like what we were thinking of, right? Like this is clearly. So this is clearly open. I mean, well, this is clearly in G. I mean. So this is in G. Like you can just say that X is a union. Let's say this is like rectangle for point P, right? For all points in X, you can say that X is a union of these rectangles, right? So like that already forms the cover. Yeah. And so one is satisfied. Now two we have to show that what if for every V1 and V2 in G. So in this case, we're saying for every AB times CD in G and A dash B dash times C dash D dash in G with a point, with a point in the intersection, right? So we'll say like a point P in the intersection of these two. I'm not called this on X. I can't even call it X. Okay, thank you. R1, R2. And the intersection of R1, R2, we can find some sort of smaller. We're saying we can find some smaller V, right? I mean, like let's draw this intuitively. If we're saying ABCD is like a rectangle that looks like this, right? And then like maybe that's like R2, for example. And then like we have the point P here, right? Then like we want some sort of smaller. We want some sort of smaller rectangle that's going to be in G as well, which includes P, which I think like this one would probably work, right? So like if we describe that like rigorously, it would just be like what? Like we want this left side to be, I guess, the max of, I don't know, like max of it'll be like max of A and A dash, right? We want max of A and A dash, comma, should be writing comma. But you get the point of what I'm trying to write, right? I might not even do it because I'm not bothered. But so A and A dash times min of B and B dash. That'll be like one of the things, right? Because like if this is A and this is like A dash, this is like B and this is like B dash. That's the intuition we want. And then the same thing with like the C and C dash. That'll be a rectangle, which is in G. It's obviously in the intersection of these two. keys in it, so it satisfies criterion 2. So it is actually a base for a certain topology, right?
You have one left.
Yes. Yeah, and also like I note that like you can actually just you could have just proven this directly as well. Like you could have directly proved this a basis in the standard topology. So like another way to do this question I'm saying is like you would say like, oh, we claim that G is a basis for the Euclidean topology. So this time we're like specifying that it's a Euclidean topology, and then like we're trying to prove that's a basis of that. I mean, yeah, like with that way, like if we take, so let's say we take like some U, like if we go with that method, right? We want to show for like we still use the same intuition of this covering thing, by the way. We're gonna find for every point inside the open set another smaller open set. Then you can just take the union of those things and it becomes a covering for that. So it's like a basis in the traditional sense, right? So if we have some sort of, so if we do it the second method, I'll do it the second method. If U is open in like the Euclidean, the standard topology, right? If U is open in the standard topology, let's say we have X is inside of U, right? Because like because U is open in like the standard topology, right? Or like in the Euclidean sense, it means we can find some sort of like ball, right? Right. Some ball, open ball, like radius R, and like maybe that's U. It should be dotted, but I'm not bothered, right? But then, like in this ball, we can kind of like we can clearly mathematically just form some sort of like square inside it. I don't know. Use like we'll say it's like if x has coordinates xy. By the way, oh, that's misleading. I should have wrote p. Like if p has coordinates xy, then like we'd want something like x plus like r onto x minus r onto times y minus r onto y plus r onto, right? Yeah, because the maximum distance between this, like, you can just like, I don't know, Pythag it, if you know what I'm saying. Is r onto even good enough? Oh, it shouldn't even be, maybe it should be smaller. Maybe let's make it like r4. Yeah, I think we'll be safe there, or something like that. Depends on what your r is as well, though. Yeah. No, it doesn't depend on what your r is. What am I saying? Yeah. So like if this is true then, right? Like if we call this rectangle I guess rectangle for P, right? Then what we're saying is like for any like we haven't specified anything for the open set. We're saying that this open set can be written as a union of R of P's. And like as you can see on the right side, it's it's an arbitrary union of open sets, so it's open. So U would also be open, and it's like covering. So we can say that the rectangles or like G is a basis. Okay. So yeah, that'll be like another method. Is it pizza here? Do you wanna should we take a break?
We should.
Yeah. Okay, sure.
I'll stop the stream for now. Unfortunately, those watching online, we can't give you virtual pizza, but hopefully this math is fulfilling for you. So your hungers. We'll be back for the final. And we'll continue the stream now. Let me check it's all up and running. Well, there's been a lot of activity in the chat. What did I miss? Mr. Open Games. My goodness. Has he said anything? Okay. It's no questions for us then.
Yeah.
Continue. When you can USB-C's out.
Yes. Yes. Yep. Okay, so we'll just continue along. Wait, how do I scroll? Oh wait, I think it's like this, isn't it? Okay. Yeah. So after that, like after the definition of basis, I think one can notice that basis, like I described it as like the smallest sort of, you want it to be kind of the smallest sort of, I don't want to say smallest sort of like open set such that like it's closed, like under unions, you get everything, right? But we haven't really talked about intersections, I guess. And like here actually specifically, like a specific example of that. So if you take any sort of subset S in the power set, the collection, which like if you see, these are just like finite, these like finite intersections of those sets. They form a base of the same topology that we were talking about above, right? So like what we like to say is that we like to say S generates this topology, or S is a subbase. So I didn't say the word generating because yeah, we use the word generating for subbases. Yeah, and like I think just go to the formal definition. It's essentially the same what we're saying. It's just like you have some sort of collection of subsets. And then you define B to be, I guess this B just forms a basis for the topology of like I guess this topology is basically you just like take the unions of this B. But yeah. Yeah, nothing particularly interesting there. I guess like the intuition just to think of why think of a definition of a subbase. It's like subbase is like the smallest set such that if my like operations is like finite intersections and unions, and I just like mix and mash all the elements inside it, I get the topology. That's like essentially what I want to think about subbase. Yeah, so we talked about convergence on a topological space previously with a sequence of points, right? So what about a sequence of functions? We can mimic the same idea. So remember that sequence of points converges to a point if each open neighborhood has some sufficiently large indice points in the sequence, right? So we can mimic this, but like we need to be a little bit careful. And like if we just go to the formal definition, what it's saying, right? So like to digest it, if you have X as a set, Y as the set of real valued functions on X, then for each X, we define this sort of scary looking thing, but it's three main parameters that we care about. The X in X, Y in R, and epsilon, right? What we're saying is like this set is the set of functions, that like make it so that at that point in X and at that point in Y, we're epsilon apart. That's like all we're essentially saying. And if we let this be, like if we let the set of all of these be a subbase, we actually do get a topology. So this topology we call the topology of pointwise convergence. Like you can kind of see like why like pointwise convergence kind of fits in here. You can actually prove it as well. So yeah, like self-explanatory with the name, like the sequence of functions where f of n xr converges pointwise to f, if and only if f of n converges to f in the topology. That's what we're trying to just basically mimic.
The reason we are not just so full, but that's specific.
Good question. Probably not. You could probably replace R with any complete, with any complete sort of, any complete field, I guess. But like, wait, like,
Well, you're using the absolute value.
yeah, yeah,
You're asking if you can do it in C instead.
yeah, maybe that's basically what he's asking.
Or just anywhere else where the absolute value is defined, or if we use some other measure of distance, since we're just saying that's all close.
Yeah, I mean, I don't see why not.
Is that a useful generalization?
I have no clue.
Let's say just because we don't really care about sequence was, let's say, good, but it makes the notation a bit more complicated.
Yeah, I mean, but C has no natural ordering, I guess. Like with respect to like some sort of absolute valuation, right? Like we don't really have like monotonic behavior. I don't know.
Move distance from origin or like.
But then like that means your epsilon here will still be a real value, right? Like you're not really expanding.
No, just
Oh, you're talking about like here. Like here, change that to C. Is that what you're saying?
change that to C, then you
And then keep the epsilon still real. Yeah, sure.
do that.
Yeah, you could do that. Yeah, I mean, there's a lot of things that I think you could do. I don't really know. Like, yeah, but good question. Yeah, and another one. This comes out in like your problem set. That's why like it might be relevant. As we discussed, we let H be a Hilbert space, like from discussing before. We say that a sequence of vectors converges weakly to a vector inside of the Hilbert space if for each vector y we have that this is true, or in like other words, like I guess like we can find some sort of capital N, like the same format of writing like there exists some capital N for every epsilon such that this is less than epsilon, or I guess the absolute value. Right? So this allows us to define the notion of a weak topology. This is basically all the same thing I just said. Yeah, so like we take the subbasis, which kind of is very similar to pointwise topology, like pointwise convergence. We take off the form of x, y, and epsilon, such that like it's like the z's inside the Hilbert space H, such that this is less than epsilon, right? And we take the weak topology given by this by using this as a subbase. Okay, so it was one of your questions to prove that a sequence converges weakly to x and h, if and only if it converges to x in the topology, right? So this proof was kind of long, but like I tried to shorten it down. But reverse direction, right? If we assume, so for the reverse, because if and only if we assume that xn converges to x in the topology, right? And we try and show that it converges weakly to x in H. We can just take, in this specific example, we can just take the open set V of, so let me write this down because it's kind of annoying, but like, let me just write down the definition again, such that n minus x, that should be the right definition, right? I'm just going to check. Yeah, and that's our subbasis, right? So if xn converges to x in tau of s, right? We want to show that xn converges to x weakly, right? Xn converges to x weakly, what do we say? It was equivalent to saying like it's true for any y, right? You can kind of just easily see that you can take in this scenario you can take v of x. No, you have to take v of xn, I think. V of xn, y, epsilon. To say like v, if you take v of xn, y, epsilon, right? By definition, this is exactly the same as saying, I guess. No, you want to take. Sorry, you want to take xn here. My bad. Yeah, and this is exactly like this y is arbitrary still, but these are things in the subbases which are obviously going to be in the topology generated by tau s. So the reverse direction kind of basically just follows. For the forward direction, what we have to do is that like for the forward direction, we want to assume that it converges weakly, and we have to show it converges to x in the topology, right? So we have to show for every open open U. I'll just say it's open. Right, with X in U. We have to find some sort of bound where after at that point, X of N's are going to be inside U. Right, like that's what we want to show. So key thing is that if you notice the finite intersections were the finite, like if you have the subbases were these V's, the finite intersections form the basis. That's what we said, right? So if it forms a basis and X is inside U, we can find some sort of element of that basis, which X will be inside, right? So this is one element of the basis. Which is going to be inside U, right? So it's like this. There's this sort of unmotivating step here, but bear with me. What we're going to do is that notice because X is inside. If X is inside the intersection of these, then obviously X is inside the individual ones, right? If X is inside this individual one, we can consider this gamma I, which will be a positive. Like I'm not going to write actually. Yeah, like it's going to be a positive number, right? And what we're going to have is that if we use weak convergence on like, because we have it as our hypothesis, right? We have that there is some sort of Ni such that xn minus x for yi, right? This yi specific will be less than gamma I, right? The key thing to here is to show that this is the same as saying, xn is inside of this, right? But then this is where x, like this one has an x here and this one has an xi here. Key thing is that you want to show that this is a subset of that. It's not hard. It's just by triangle inequality. Like if you have S is inside of gamma I, what is that saying? That's saying that S minus x of that is less than or equal to gamma I, right? We want to show that if this is inside this, we want to show that S is inside of y by epsilon I, right? So if we consider the inequality here, I mean not the inequality, the inner product, then we can have a by triangle inequality, we can say that this is the same as decomposing it to x plus, that's so, right? But this one, we have that's bounded by gamma I plus, right? But gamma I was defined as epsilon I minus precisely this, right? So this will be epsilon I. So yeah, we clearly have that S is inside here. So this means that xn is inside of all of these for all n greater than or equal to ni, right? So we use the same trick where we take the max, we take some really large L, which is the max of all of these n1s, n2s to ni's. Then xn, where n is bigger than or equal to L, is going to be inside all of these vxi, yi, epsilon i's, right? It's going to be inside all of these, which is clearly what I wanted, because now that means xn is inside U for all n bigger than or equal to L. So yeah, that was a bit of a terse question. I mean, like not yeah, like it was a bit like dense, but like run through it again while you're practicing for your exam, I guess. Yep. So we have this sort of generalization, we want to basically have some like this. The next definitions are like generalizing the, I guess, idea of taking a limit. Just to quickly just define what nets are here. It says like it's a directed set, right? It's a directed set, which has a binary relation, which satisfies reflexive, transitive, and this is a key thing, I guess. Here, this is pretty important actually. Sometimes there exists some sort of M such that for all pairs I and J, we have that I and J has some sort of M that bound above it. So this is the upper bound property for pairs of elements. Another way to call it is that it means that this set has joins. So like that's like another phrase. It's joined, has joins, or it's like join complete or sub complete is like one another way you'd say this. Here, like, yeah, how you can view like your normal sequence when you take it the limit, you're taking it as a function from the natural numbers to some set x, right? What we're going to be doing is we're going to be doing the same thing, but now our indexing is not natural numbers, but it's the elements inside the directed set. So yeah, we can view it as like a function from the directed set to some set x. The way we map an element from this like directed set to x is what we call a net, essentially. That's just it. Yes, and the definition that we have is that if you let X be a topological space, a net converges to a point if every neighborhood V of X, there exists some sort of alpha V, which is inside the directed set, such that for all lambda greater or equal to alpha, we have that X lambda is in V. Okay. I don't have any questions about nets, but yeah, I couldn't really find any questions in the sheets as well. So yeah, we'll probably skip that for now. To the one important thing now, homeomorphisms. So literally a big question of every mathematician is when are the two spaces more or less the same, right? And as Jeff was talking about, the tongue-in-cheek classic example is that we can say a coffee mug and a donut are the same topologically, right? But like we want to define what it means to be the same, right? And given two topological spaces, what definition do we want to be the same? And I think we said this repeatedly today, but like all the essential informations about topological spaces are in open sets. Like if you think about a topological space is literally just a normal set, but with a description of open sets. So the key informations are the open sets, right? What we want, like, and the maps that we care about, the continuous maps that we really cared about was ones which were preserving open sets when you take the inverse, right? So if you want like a bijection of topological spaces, you want a bijection of their sets, but you also want that their open sets are preserved in both ways. That's the definition of homeomorphism. So yeah, the homeomorphism, like a bijection f of x to y is called a homeomorphism if both of their functions, forward and backwards, are continuous. We say that x and y, the spaces are homeomorphic if there exists a homeomorphism. Okay, so homeomorphic invariants, these are very important because obviously if you show homeomorphic invariants are obviously like top properties which stay invariant under homeomorphism, right? If you show two spaces have one space has a certain homeomorphic invariant but the other space doesn't, then we know automatically that they're not going to be homeomorphic. So connectedness. But if you think about it, anything that you phrased in terms of open sets will become a topological invariant or homeomorphic invariant. So like connectedness, which we'll define now, notice that the definition will be only in terms of open sets. Hausdorff will also be a topological invariant. Compactness, which we'll define using open sets, that's also going to be a homeomorphic invariant. But like boundedness, as you saw before, boundedness is not like these are invariants, these are not, right? Boundedness does not take like R, the real number, and the open interval 0, 1. There's a very famous homomorphism that you can take from this to this. You can use some sort of tan inverse stuff and like shift it over. So these are homeomorphic, just take that as granted, but you can see one of them is bounded and one of them is not. Right. And boundedness has nothing to do with open sets only. So yeah, we really care about the intrinsic properties that are only using open sets in topology. So let me say the definition of connectedness. A topological space is connected if it is not the union of two disjoint non-empty open sets. Okay. Yeah, as you can see, it's like you can see the definition only use open sets, which is what we really want in topology. This is a fun, motivating problem. It's not that hard. If you have X as a topological space, X is disconnected Oh, by the way, not connected is just disconnected. X is disconnected if and only if there exists a non-constant continuous function of x to 0, 1. This is, by the way, just has a discrete topology. Yeah. So why is this a motivating problem? This is a motivating problem because we can show that the topological property of disconnectedness actually has something to do with their maps between topology spaces. So this is like another key idea, but like it's not that important right now. Yes. So yeah, as I said, connectedness is topological invariant. We also have that if f of x to y is a continuous function, if x is connected, then so is f of x. So this one is forward. So I won't prove that, but yeah, just take that for granted. Another one is path connectedness, and a topological space is path connected if for every pair of points, x and y, there is a continuous function from 0, 1 to x, such that f of 0 is x and f of 1 is y. So this is probably the one that we're more used to say something is connected, that you can actually have paths going between it, a continuous path going between it, right? But as you can see, this one doesn't only use open sets. So it's actually not an intrinsic definition that we really like. So that's why connectedness exists. But yeah, if path connectedness is true, this implies connectedness. Sketch of the proof. Okay, let's assume we have path connectedness, and let's say it's not connected. If it's not connected, then we can write like the X as like a disjoint union of open sets U and V, right? The key idea should be that like there is no path from U to V. Like there's no continuous path from U to V. And why? Say there is a continuous path from U to V. So let's say like little u is in big U, little v is in big V. Let's say there's a continuous path, gamma. So there's a continuous function from 0, 1 to x, such that this is this, this is this. Key idea is that you want to show that the pre-image of U and the pre-image of V is equal to 0. Yeah. So like this is just coming from the fact that if you take the pre-image of x with respect to the continuous function gamma, you would get 0 to 1, right? But pre-image of x, you can pretty easily show that you have this disjoint union of pre-image of U and pre-image of V. The fact that gamma of U is equal to U, gamma of 1 is equal to V, shows that these are both non-empty. Right? And these are going to be clearly disjoint. You can just check that. And as you can see, then this is a contradiction because 0, 1 is clearly connected. Like this is connected as in the definition that we said earlier. This is connected, but we showed it as a disjoint union of non-empty open sets. So this is a contradiction. Yeah, so we just proved that path connectedness implies connectedness. Yeah, so some example problems, we'll go through these quickly because they're pretty relatively short. Prove that x, r excluding 0 and r squared excluding 0, 0 are not homeomorphic. That's the same thing. Well, obviously y is connected, right? Because like it's a 2D plane. If you just exclude this little thing, anything can like kind of just move around it, right? So there's it's like the fact that you can move around it means that you can have a continuous path, right? So it's path connected, which implies it's connected, right? So y is connected, but clearly in the open line, if you exclude this 0, then anything here and anything here you can't. It's not path connected, right? I mean, okay, well, no, we're not working in the projective plane, so we can't do that. But yeah, so x is not connected, y is connected. So as we say, they can't be homeomorphic. And to use that to prove that r and r squared are not homeomorphic, you can do the same where you kind of just remove a certain point. So if you think about a homeomorphism between r and r squared, if there exists one, and you consider the restriction where you take r squared away with the origin, and r, you take it away with the preimage, right? This will still be a homomorphism where the former, as in this r, is clearly homomorphic to this. As in like, this one is going to be like r with a point removed somewhere. we're saying it's homomorphic to R removed with the point like at 0. Why? Just think of like a homomorphic function where you just shift it by that amount, right? You get what I'm saying, right? Like this one removed. Homomorphic function just like x to like x plus a. And then the inverse is clearly continuous. Yeah. Okay, finally we got to compactness. So compactness is really important because yes, it deals with the notion of finiteness. And what we mean by that is everything we said about like basis and like coverings. We said like there exists a covering, right? The indexing set never had to be finite. But if we want to deal with finiteness, that's essentially just what we're saying, like, oh, these are compact spaces. So yeah, the definition is that's literally what I said. If you take a topological space, it is compact if every covering, right, here, this is like an open covering. Every open covering, there is a finite subset, which is, I guess, yeah, like indexed by natural numbers, such that these already cover X. So like a subset Y of some X is compact, if and only if it is compact in the subspace topology. So if you want to show that it's compact, you should be probably using this instead in the definitions. That's basically just saying, that's just it. Like it's saying like this definition to show subset Y is compact would just be like, instead of this being equality, you would have it as like covered because it's subspace topology. That makes sense, right? Yep. So yeah, a clear example is that 0, 1 is compact. Yeah, but you can just think about that. That's there's a finite covering for that. These are some key important properties. How much time do we have?
3 minutes.
These are actually some pretty important properties. This second one was, I'm pretty sure, my finals question, like in 3611. I doubt he will put it again. Maybe he would, but yeah, if I just run through it really quickly, right? So if we have X as a compact topological space and Y is a closed subset of X, then Y is compact is what we're saying. The hint, there's literally a hint given here, and it's saying like you can add YC, which is like the complement of Y, as an open cover for Y. Like, say you have some sort of open cover for Y, right? So you have an open cover for Y. You can just add the complement of Y, and that becomes a cover of X. Right? As we said, like X is compact, so every cover of X can have like a subset of the cover, which is just finite, and that's already enough, right? But if that's finite, then the open cover of Y will also obviously be finite. So that's why Y is compact. That's like a quick proof. That makes sense, right? Nothing wrong there. This second one's actually a little bit more complicated. This is the one that was on the test. It's saying like if X is a Hausdorff topological space, and if Y is an X, is a compact subset, then Y is closed, right? So like you notice how like the assumptions changed actually, but the thing was reversed. Like not reversed, but like they switched around. The proof of this is actually you want to show that X excluding Y is open is the main idea for this one. And well, like it uses the same idea where if we want to show this is open, we'll like take any arbitrary point and we're going to find some sort of open set, which is including X and inside this. So like say we fix some sort of X here in X excluding Y, or the complement of Y, I guess, whichever one you like. Note, because Y is compact, right? We will have some sort of finite covering, right? So let's say we have some sort of finite covering U I is 1 to K of Y, right? If we fix some sort of X in this, then we take any Y in. Actually, wait. Maybe this step should have been actually afterwards. Actually, yeah, we'll do this afterwards. Fix some sort of X, and let's say we take some sort of Y and Y, right? clearly x and y are not the same. And we have the x is Hausdorff, right? Since x is Hausdorff, we can find some sort of open set U, V, intersection is empty, such that x is in U, y is in V. Right? We can take like this open set of y and v. We can take all of those, and that forms a covering of y, right? Let's say that's vy, little y and y. Because it's compact, we can because y is compact, we can take this down to a finite finite covering like this, right? So now instead of just being over all of the y's, it's now finite, right? But notice if we think about the corresponding u that was corresponding to that for that x, right? We have like u of 1, u of 2, u of k. These u's are like defined here, right? What we can do is that we can take the intersection of all of these and this is going to be still open and it's going to contain x. The key claim is that this is going to be an open subset of x excluding y. And the reason why is because like it literally follows from construction. Like if this does include a point of y, right? If this doesn't, like if this has a point p, which is also in y, because p is in y, we said that p is going to be in some sort of basis element of this cover, right? So p will be inside some sort of vy of j, right? But then p is inside all of this, which means p is also inside uj. So they're inside these two intersected together. But by construction, these were supposed to be empty. So that's a contradiction. So the key thing is that this is open. We found the open subset of x complement y complement for every point in x by y complement. So we get that this is open. Does that make sense? Yep.
We then get that if a topological space is Hausdorff and Compactness closed.
Yes, that would be right. Yes, if you have a but then wait, for like to say a topological space is closed, like a topological space is obviously closed in itself, right? Because the empty set is open. So like that wouldn't be something that's useful. Yeah, like you would want it in some sort of embedding, yeah, like this scenario. Yeah. Yes. So applying this, let's apply the thing that we just proved for 2018 Q3. Like we literally just did all the hard work. This one says prove that if y is a subset of x which is compact, and this is continuous, then f of y is a compact subset, right? Yeah. So oh wait, there's actually more questions. Yeah. Just consider any open cover of f of y, right? We had that x for each vi in tau dash. We let ui be f inverse of vi, right? Which is going to be open as v is continuous. So ui forms an open cover of y, right? But since y is compact, each open cover of y has a finite subcover like this. So taking it back, the image which was vk, which were all open, clearly form a finite subcover of fy. So fy is also compact. That's one way you can do it. And he says show that suppose that y dash is a compact subset of x dash, and f of x to x dash is continuous. Is S inverse of y dash necessarily compact? This is actually the same. This is like essentially the same question as like the thing that we had above, and we use the same example. You can take the function from real to real, standard topology, constant function at 0. Then you have that f inverse of 0 is R, which is not bounded, so it's not compact. Yeah. Yeah, this one's where we use it a lot, actually. So if X is a compact topological space and Y is Hausdorff, right? This one's compact, this one's Hausdorff. Then if you have a continuous map and Z is closed, then you can actually show that f of z is closed. So this was an example that from before we said like the image of something doesn't necessarily like we had opens get preserved by key images, right? But they don't necessarily get preserved through images. This one's an example showing that if you have compact, the image is preserving that open or closedness. So like we did actually all the hard work. Yeah. If x is compact and z of x is closed, right? So we have that z is compact from before, right? That was one of the things. F is continuous, so it follows that f of z in y is compact. That was also one of the things before. But y is Hausdorff. So if y is Hausdorff and f of z is compact, we had that f of z has to be closed. That was one of the things as well. So yeah, these three things just used all the things that we actually talked about. And then this one, show that if f of x to y is a continuous bijection, there is a homeomorphism. So it's a continuous bijection continuous bijection obviously doesn't necessarily imply a homeomorphism because the inverse might not be continuous, right? So we just have to show the inverse is continuous here. Yeah, it's pretty routine, this one. You just define the inverse. We want to show G is continuous, as in if Z is closed in this, then the inverse of the inverse is closed. Yeah, it's like you just do a bunch of definition chasing. It's not that important. Yeah, I think we basically got through all the main important ones. Heim-Borel theorem. Yeah, so from now on, there are going to be a bunch of theorems which I'm not going to prove because I don't know how to prove them. And they're long. And also, I think like after this point, not many of the topics here is going to be included in your problem sheets when I looked at your problem sheets. Yeah, so take that with a grain of salt though. Like I'm not going to take responsibility if Heim-Borel theorem actually comes out in your exam, and like you can't say that Daniel said there won't be Heim-Borel theorem. But yeah, you can just know the statement. The statement is that if you have X is compact, this is like if and only if X is closed and bounded. So that should be true of your intuition in like metric spaces. I think metric spaces we defined compact as closed and bounded. So it's not that surprising, but it is a theorem. This compact, but like notice that this compact is the different definition now. It's a definition only using open sets. And Bolzano-Weierstrass theorem, our trusty Bolzano-Weierstrass theorem, everybody knows it, right? So every bounded sequence of real numbers has a convergent subsequence. Yeah. So these are some important ones. Like this is probably the last example that's important. Consider x1, which is this. This is I wrote it like this, but essentially it's just a circle, right? If you look at it, topologically it's just a circle. So we can think of it as an R squared as well. It doesn't really matter. This one, as you can see, this one's going to be something that looks like it's going to be like something that looks like this, right? If you like, I might be wrong by the way, but both with the usual metric topology, right? So we want to prove that x1 is not homeomorphic to x2. Notice, as I said, compactness is going to be a homeomorphic invariant or topological invariant. This one is a circle. You can see that it's closed and it's bounded. So because it's closed and it's bounded, it's compact. And like this one, you can claim that it's not bounded because you can find something, you can keep finding something. So it's not compact. And we're basically done. So yeah, like the Heim-Borel theorem was used here. The Heim-Borel theorem was used to show that closed and bounded implies compactness. Okay? That makes sense, right? Yep. We say a topological sequence is sequentially compact if every sequence in X has a convergent subsequence. That's like essentially the precondition of Bolzano-Weierstrass. Like it's nothing that too crazy. But I guess we have that all of these three are equivalent. Heim-Borel theorem already showed that these two are equivalent. Yeah, I think this is actually not too bad. Like Heim-Borel theorem already showed that these two are equivalent. Technically, Bolzano-Weierstrass shows this to that. But in the case of R, we haven't extended it. But like if you extend it and you accept that's true, then yeah, this will happen. I guess all you need to show is sequentially compact implies compact or closed and bounded. I think this direction is probably easier, but like, yeah, there's a way to show it. And we don't have to prove this, but yeah, take it as a fact that these are all equivalent. Yeah. This is something that this is something we already proved. Yeah, extreme value theorem is something that it's like a special application of what we already thinking about for compactness, right? Yeah, we can basically skip that. The Hein-Cantor theorem, yeah, this one might be a bit important. So recall that we say something is uniformly continuous if like we don't have to specify the specific point. All we need to do is specify an epsilon value, and that epsilon value we have a delta value which covers it for over all, I guess, points is like the intuition, right? As you can see, for all epsilon, you choose an epsilon, there exists some sort of delta such that this is globally true, right? We don't have to choose at some sort of x. So Hein-Cantor theorem says that if we let xd be a compact metric space and let f of xr be a continuous function, then f is actually uniformly continuous. So yeah, a compact metric space, like just because if you have continuous over already, then you can actually just generalize it to saying that we'll have some sort of supremum delta is actually basically the proof. Yep. We have a concept of totally bounded, and we say a metric space is totally bounded if for every epsilon greater than 0, there's a finite set such that we can cover it with like these open balls, essentially, right? Notice it's kind of similar to, I guess, the compact definition. The compact definition we cover with open sets though. So those open sets don't necessarily have to be bounded. But yeah, here we have this fact of totally boundedness. Yep, notice that if y is totally bounded, then every subset of y is also totally bounded. That just kind of follows through using subspace. Similarly, the closure of y is also totally bounded. Yes, so this is a pretty important characterization. If this is like the generalization of what we had before for Rn, but like in any metric space. If we have X is a metric space, then all of these are equivalent. Notice that the last one is a bit different though, because we have to replace closed and bounded with complete and totally bounded. That like Y, just read the proof. Like there's certain properties in the proof that you need it. Yes. Okay, yeah, here's where it really doesn't matter. Equicontinuity. There's like the definition of equicontinuity. You have pointwise equicontinuous if for every point x and epsilon greater than 0, there exists some sort of delta such that for every f in S, we have that the distance between these, whenever the distance is between these, right? Uniformly continuous, you just drop the point for every point. You can have a global delta for a certain epsilon, right? So this is a pretty amazing theorem, which I don't know the proof at all, so don't ask me. But Arzela-Ascoli theorem says that if you have these two metric spaces where one of them is compact, then S is pointwise equicontinuous if and only if S is uniformly continuous. So yeah, like it's like the same analog of like what we had before, like the where is it? Yeah, the Hein-Cantor theorem. Right. Yes. So this is like just a usage of it. A bounded subset of, I guess, continuous functions on 0, 1 with the infinity norm is totally bounded if and only if it's equicontinuous. Yeah. I think this is the last theorem that we'll probably look at. Am I right? Oh no, the second last theorem. So the Weierstrass approximation theorem says that if we look at the metric space CAB endowed with the, I guess, the infinity norm, then over a closed bounded interval, you can always find some sort of polynomial such that for the infinity norm, we're epsilon away from it. Hopefully that's not too surprising, but like, yeah, it's not trivial, but we do have an intuition that polynomials Taylor series and Lorentz series and polynomials can approximate most smooth functions as nice as we want, right? So this shouldn't be that surprising, I guess. A question which uses that. So let's say we denote P as a set of polynomials which lie in V, and V is just the smooth functions which have an integral of 0, right? So give an example of a non-zero element in P. I mean, the integral is 0. It doesn't imply it has to be 0, right? You can just take like x minus the half, right? That obviously has signed integrals, a signed area of 0. It says what is the closure of P, right? By the Weierstrass approximation theorem, because like we're epsilon away from everything, we should probably have some sort of guess that it might just be P, V, I mean, the closure of P. And that is indeed true. But the Weierstrass, here's where the Weierstrass approximation theorem gets used. It guarantees that there is a polynomial, but it doesn't mean that that polynomial is inside V, right? As in the area of the polynomial is equal to 0. We don't know that, right? But we can actually bound if we do some inequalities, right? Yeah, these are all pretty self-explanatory. This is triangle inequality. This is the one that we talked about where we take it inside, the integral inside, and it's still bounded. We have that the area of this integral for the polynomial that we chose will be less than epsilon on 2, right? So if we let C be this integral, and we just consider the polynomial where we take that polynomial minus the area area for this polynomial will obviously be 0, right? Which means that we can use that as one of our candidates, because all we can do is we can use the infinity norm and then the triangle inequality, where at worst we'll get epsilon 2 and epsilon 2, which will give us epsilon. And epsilon was arbitrary, right? So yeah, P is dense in V. And then the last question was that, is this complete, right? And I mean, obviously, like we have that this is complete. Like C, we know that C01 with the infinity norm is complete, right? So it just suffices to show that this is closed. But V is the closure of P. So obviously, we just showed it was closed. Yes, I think, yes, this is like the last year. So separation of points, we say if we have x and y be two sets, we say a set S of functions between x and y is set to separate points if for distinct x and y and x, there is a function f and s such that f of x is not equal to f of y. As in the functions themselves can distinguish whether the 2 points are not equal, right? So Urson's lemma says if x is a Hausdorff and compact space, then CXR separates points. Yeah, just take that as granted. And recall that an algebra of functions is a vector space of functions which also has a multiplication property, which is pointwise multiplication, right? A unital algebra is an algebra that also contains the unit constant function y. Yeah, this is all just definitions, but like you can think of the polynomial ring as like a very simple algebra. Yeah. A Stern-Weierstrass theorem says that if X is Hausdorff and compact, and we have A is a unital subalgebra, then we say that A is dense with respect to infinity norm if and only if A separates points. So, yeah, I think it's just best to use to give an example of a usage of this one. So, yeah, this is a 2019 Q9 problem, and it says like if S is the span of these functions, the exponential functions, what are the interior, the boundary, and the closure of S in the uniform norm? So yeah, what we're supposed to notice is that S is a candidate of a unital subalgebra. So yeah, it's like if you think of it as like the span, as in these are like the infinite dimensional basis, then you can see it's a unital subalgebra. T either to T. As you can see, like the pointwise multiplication, they always stay within each other because there's just going to be exponentials. We have that 0, 1 is Hausdorff and compact. That was already from before. We also have that FK of T, which is EKT, is injective. So it can separate two distinct points, right? So actually any function can actually separate the points. So Stern-Weierstrass applies, which means that the closure of S is C01. That answers one of it. The interior is empty because what does it mean to be the interior? The interior means that like there exists some sort of open set such that the whole open set is contained inside of S, right? But if you accept the fact that like if any finite sum of either the KTs can be approximated like as well as you want using like a Taylor series. Now, the Taylor series would just be like a sum of polynomials. And you're working over something which is the compact interval 0, 1. So you can make it as good of an approximation as you want over all the points, which means like with respect to the infinity norm, you can get as close as you want to it. So yeah, the interior is empty. And so the boundary, if you use the property that we had, would just be the whole space. Yeah. Yeah, I think that's it. I think we can end it there. I think we basically covered everything that was necessary. So yeah.
Okay. I'm going to end the stream now. Can I just get everyone to just stay back for just 1 more minute? Can we get a photo with the banner with everyone?